For centuries, humanity has sought to understand the subtle whispers of the cosmos, the faint echoes of events that shaped the universe itself. In this pursuit, the discovery of the gravitational wave background, GWB, has emerged as one of the most groundbreaking achievements in modern science. These ripples in spacetime, created by some of the most violent and ancient processes in the universe, carry a story older than stars, a story etched into the very fabric of reality. Join us as we explore the journey, the science, and the profound implications of uncovering this cosmic symphony, from the earliest theories to the cutting-edge technology that made detection possible. Origins of gravitational waves. Gravitational waves are ripples in the very fabric of spacetime, first predicted by Albert Einstein in 1916 as part of his general theory of relativity. These waves travel at the speed of light, carrying with them information about their cataclysmic origins, such as black hole mergers, neutron-star collisions, or even the explosive birth of the universe. While the first direct detection of gravitational waves by LIGO in 2015 marked a monumental leap in astrophysics, these detections only scratch the surface of a much broader phenomenon: the gravitational wave background, GWB. The GWB is a faint hum of gravitational waves that permeates the universe, created by the combined effect of countless overlapping sources. Unlike discrete events such as black hole mergers that produce sharp, identifiable signals, the GWB is the cosmic symphony of spacetime, its notes blending into a continuous background of vibrations. Think of it as the difference between hearing a single bird chirping in the forest and listening to the ambient rustle of the entire woodland. This enigmatic background holds clues about the universe's deepest mysteries. By studying it, scientists hope to unlock answers to questions about the formation of galaxies, the nature of dark matter, and even the birth of spacetime itself. But what exactly creates this persistent cosmic hum? To understand that, we must delve into the sources of gravitational waves, ranging from the colossal to the microscopic. At their most basic level, gravitational waves are produced when massive objects accelerate asymmetrically. Picture two celestial bodies locked in orbit, such as a pair of black holes spiraling toward each other. As they move, they disturb spacetime, creating waves that ripple outward like ripples in a pond. When these black holes finally collide, the event releases an enormous burst of gravitational waves, an explosion in the spacetime continuum that travels across the cosmos. However, the gravitational wave background isn't limited to these dramatic moments. Instead, it builds up from more subtle, cumulative sources. For instance, in the early universe, as matter and radiation interacted during the period of inflation, quantum fluctuations may have generated primordial gravitational waves. These waves, fossilized in spacetime, still resonate faintly today. Similarly, populations of merging binary black holes and neutron stars contribute to the GWB, their collisions happening so frequently across the universe that their individual signals blur into a collective hum. Even more exotic sources, like cosmic strings, hypothetical defects in the structure of spacetime left over from the Big Bang, could contribute to the background. As these strings vibrate and snap, they might emit gravitational waves, adding their distinct frequencies to the mix. This cacophony makes the GWB an extraordinarily rich field of study, but also an immensely challenging one. Detecting gravitational waves is a feat of engineering and ingenuity. Gravitational waves distort spacetime, but the distortions are minuscule, on the order of a fraction of the width of a proton over kilometers of distance. To detect these waves, scientists use sophisticated interferometers like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo. These devices use laser beams to measure incredibly tiny changes in the distance between mirrors, which occur when a gravitational wave passes through Earth. While this method works well for detecting sharp, transient signals like black hole mergers, it is less suited for the continuous, faint hum of the GWB. The background is subtle, blending into the noise of the instruments themselves. To isolate it, scientists rely on statistical methods, analyzing years of data to find patterns and correlations that might reveal the presence of the GWB. The GWB is stochastic, meaning it is a random, persistent signal with no single identifiable source. This randomness arises from the sheer number of overlapping waveforms, each originating from a different cosmic event. Yet, this stochastic nature is also its strength. By analyzing the statistical properties of the GWB, such as its power spectrum, which describes how energy is distributed across different frequencies, scientists can infer information about the types and distribution of its sources. For instance, if the GWB contains significant energy at low frequencies, it might suggest contributions from supermassive black hole binaries, whose gravitational waves are slower and longer lasting. Conversely, high-frequency components could point to exotic phenomena like cosmic strings or even high-energy events from the early universe. The GWB acts like a universal fingerprint, holding clues about both the past and the ongoing processes of cosmic evolution. The gravitational wave background is more than just a scientific curiosity. It is a window into the unseen and the unknown. By studying the GWB, researchers can access information that is otherwise inaccessible through traditional methods of astronomy, such as observing light or electromagnetic radiation. For example, the GWB can reveal hidden populations of black holes and neutron stars that are too faint or distant to be detected individually. It can also provide insights into the history of galaxy formation, since the collisions of black holes and neutron stars are closely tied to the evolution of galaxies. Moreover, by studying primordial gravitational waves, scientists hope to probe the earliest moments of the universe, potentially validating or challenging models of cosmic inflation. Beyond astrophysics, the GWB offers a testbed for new physics. Gravitational waves interact weakly with matter, meaning they can travel across the universe virtually unimpeded, preserving information about their sources. This property makes them ideal for studying phenomena like dark matter and dark energy, which remain among the greatest mysteries in modern science. The study of the gravitational wave background is still in its infancy, but the future is bright. As detection technology advances, scientists are developing new methods to filter out noise and improve the sensitivity of instruments like LIGO and Virgo. Meanwhile, upcoming missions like the Laser Interferometer Space Antenna, LISA, promise to revolutionize the field. Unlike ground-based detectors, LISA will operate in space, free from terrestrial vibrations, allowing it to detect low-frequency gravitational waves with unprecedented precision. In addition to hardware improvements, advancements in data analysis are playing a crucial role. Machine learning algorithms are being trained to sift through vast datasets, identifying patterns that might indicate the presence of the GWB. Meanwhile, international collaborations are pooling resources and expertise, creating a global network of gravitational wave observatories that can work together to detect and analyze the faint hum of the background. Studying the gravitational wave background is not just about understanding the cosmos, it's about understanding our place within it. The GWB connects us to events that occurred billions of years ago, offering a direct link to the history of the universe. As we listen to the hum of the universe, we are not just uncovering its secrets, we are expanding the boundaries of human knowledge. The gravitational wave background is a testament to the ingenuity of scientists and the infinite complexity of the cosmos. Theoretical foundations of gravitational waves. The concept of the gravitational wave background, GWB, is deeply rooted in the theoretical framework of Einstein's general theory of relativity, cosmology, and the evolving understanding of astrophysical phenomena. Unlike individual gravitational wave events such as black hole or neutron star mergers, the GWB represents a cumulative hum of gravitational waves produced by innumerable cosmic events across the history of the universe. This omnipresent signal offers a profound opportunity to explore the universe's hidden dynamics, from its earliest moments to the intricate interactions of its largest structures. According to general relativity, the acceleration of massive objects distorts spacetime, generating ripples that propagate outward at the speed of light. These ripples, gravitational waves, arise not only from isolated events, but also from the overlapping contributions of countless sources throughout cosmic history. The realization that the universe is saturated with such signals forms the foundation of the GWB. At its core, the GWB is a stochastic signal, meaning it lacks the coherent structure of individual gravitational wave detections. Instead, it is a persistent, random noise-like signal, produced by the superposition of waves from a variety of sources. Its existence is a testament to the vast and varied mechanisms driving gravitational wave production, ranging from astrophysical sources like compact binary mergers to cosmological phenomena tied to the universe's birth and evolution. The GWB is primarily formed by astronomical phenomena, most notably compact binary mergers. The inspiral, collision, and merging of neutron stars, binary black holes, and other similar phenomena fall within this category. These kinds of occurrences cause enormous gravitational waves to ripple through space and time. The GWB is a result of the overlapping and merging waves from numerous mergers spanning billions of years. The rate of binary formation, the mass distribution of the objects involved, and the cosmic development of galaxies where such events occur are the parameters that models propose as determining the frequency and intensity of this backdrop. Interactions between supermassive black holes, SMBHs, are another important source in astronomy. The center stellar mass black holes, SMBHs, of merging galaxies slowly spiral inward, producing gravity waves with low frequencies as they draw closer to coalescence. Given that pulsar timing arrays pick up on the lower frequencies linked with GWB, these signals are especially important for those GWBs. There are contributions from rotating neutron stars. If such stars are slightly asymmetric due to mountains or deformations in their structure, they emit continuous gravitational waves. Though weaker than merger events, the cumulative effect of many such sources adds another layer to the GWB. While astrophysical sources provide a more familiar context, the cosmological origins of the GWB are perhaps even more tantalizing. Theoretical models suggest that gravitational waves from the early universe could be imprinted in the background. These signals carry information about processes that occurred fractions of a second after the Big Bang, long before the formation of stars and galaxies. One of the most significant contributors could be primordial gravitational waves generated during inflation. Inflation, a period of rapid expansion immediately following the Big Bang, stretched quantum fluctuations in spacetime to macroscopic scales. These fluctuations produced gravitational waves that permeated the universe. If detected, these waves would provide direct evidence for inflation and offer insights into the energy scale and mechanisms underlying this mysterious process. Phase transitions in the early universe are another potential source. As the universe cooled, it underwent transitions akin to water freezing into ice, breaking fundamental symmetries and creating phenomena like cosmic strings. These topological defects, if they exist, would generate gravitational waves as they oscillate and decay, leaving a distinct imprint on the GWB. Understanding the GWB requires exploring its frequency spectrum, which reflects the diverse sources contributing to its makeup. Different events produce gravitational waves at specific frequencies, resulting in a complex signal spanning multiple ranges. For instance, compact binary mergers predominantly emit in the high-frequency range, detectable by ground-based observatories like LIGO and Virgo. Supermassive black hole binaries produce low-frequency waves, best observed through space-based observatories like LISA or Pulsar timing arrays. Meanwhile, cosmological sources like inflation are expected to produce extremely low-frequency waves, requiring novel detection methods such as cosmic microwave background polarization studies. The spectral properties of the GWB also encode information about the universe's evolution. The amplitude and shape of the spectrum can reveal the density of sources, their energy scales, and even the conditions under which they formed. For example, a sharp feature in the spectrum might indicate a specific phase transition, while a gradual slope could suggest a continuous contribution from astrophysical mergers. Detecting the GWB presents unique challenges. Its stochastic nature means that it does not exhibit the distinct chirp patterns of individual gravitational wave events. Instead, it appears as a persistent random signal superimposed on detector noise. Identifying the GWB requires sophisticated statistical techniques that analyze long-term data and correlate signals across multiple detectors to distinguish the background from local noise sources. Terrestrial noise is a significant obstacle. Gravitational wave detectors are sensitive to vibrations, seismic activity, and even atmospheric disturbances. Advanced noise mitigation strategies, such as isolating detectors from environmental influences and employing machine learning algorithms for signal processing, are essential for teasing out the faint signature of the GWB. Cross-correlation techniques are particularly important. By comparing data from detectors at different locations, researchers can identify consistent patterns that indicate a gravitational wave origin. This method not only enhances sensitivity, but also helps separate the GWB from transient astrophysical events and terrestrial noise. The detection of the GWB would have profound implications for fundamental physics. It would provide a direct test of general relativity in the regime of weak continuous waves, complementing the high-strain events observed from mergers. Additionally, the GWB could shed light on the nature of dark matter and dark energy, as these mysterious components of the universe influence the propagation of gravitational waves. Furthermore, the GWB might offer clues about the quantum nature of gravity. Theoretical models that attempt to unify general relativity with quantum mechanics predict subtle deviations in the behavior of gravitational waves. Detecting such deviations in the GWB would open a new frontier in theoretical physics. Pulsar timing arrays, PTAs, are among the most promising tools for exploring the low-frequency component of the GWB. By monitoring the timing of millisecond pulsars, highly regular cosmic clocks, PTAs can detect tiny perturbations caused by passing gravitational waves. These efforts have already yielded tantalizing hints of a low-frequency GWB, potentially from supermassive black hole binaries. PTAs operate over timescales of decades, requiring patience and precision. The accumulation of data improves sensitivity, allowing researchers to probe weaker and more diffuse signals. The ongoing efforts of projects like Nanograv and the European Pulsar Timing Array are crucial in this endeavor. Beyond its scientific value, the GWB carries profound philosophical significance. It represents the universe's collective memory, a record of its dynamic processes etched into spacetime itself. Listening to this cosmic symphony connects us to events that occurred billions of years ago, offering a perspective that transcends individual events and highlights the interconnectedness of cosmic phenomena. The GWB also challenges our notions of observation and discovery. Unlike the visible or electromagnetic universe, the gravitational wave background is a silent, unseen realm that requires us to rethink how we perceive and interpret the cosmos. Its discovery would mark a milestone in humanity's quest to understand the universe, bridging gaps between theory, observation, and imagination. The theoretical foundations of the GWB provide a roadmap for unraveling some of the universe's most profound mysteries. From the interplay of astrophysical and cosmological sources to the challenges of detection and the implications for fundamental physics, the study of the GWB exemplifies the dynamic and interdisciplinary nature of modern science. Historical efforts to detect gravitational waves. The journey to detect gravitational waves has been one of the most ambitious and transformative endeavors in modern science. From early theoretical predictions to the groundbreaking observations of today, this field has progressed through a mix of ingenuity, perseverance, and collaborative efforts. This section explores the historical milestones, technical innovations, and societal impacts that shaped gravitational wave detection. The concept of gravitational waves originated from Einstein's general theory of relativity in 1915. While Einstein himself doubted that these ripples in spacetime could ever be detected, the idea captivated physicists who saw in it a way to probe the universe's most extreme events. The first serious attempt to detect gravitational waves began in the 1960s with Joseph Weber, a physicist who designed resonant bar detectors known as Weber bars. These large aluminum cylinders were intended to resonate in response to passing gravitational waves, producing detectable vibrations. Despite Weber's initial claims of success, subsequent experiments could not replicate his results, casting doubt on the feasibility of such detectors. However, Weber's pioneering efforts inspired a generation of researchers to pursue the challenge with new techniques and technologies. The development of laser interferometry in the 1970s marked a significant turning point. Unlike resonant bars, laser interferometers use beams of light to measure incredibly small changes in distance caused by gravitational waves. Rainer Weiss, one of the co-founders of the Laser Interferometer Gravitational Wave Observatory, LIGO, proposed the concept of interferometric detection. His visionary work laid the groundwork for future experiments, but the path to success was far from straightforward. Early prototypes faced severe challenges, including isolating the detector from seismic noise, thermal fluctuations, and even quantum effects like photon shot noise. Skepticism was widespread within the scientific community during the early decades of gravitational wave research. The detection of such faint signals, with strain amplitudes on the order of 10 to 110 minus 21 1021, seemed almost impossible. Critics argued that noise from terrestrial sources, such as ground vibrations and atmospheric disturbances, would overwhelm any potential signal. Yet, researchers persevered, driven by the promise of opening a new observational window to the universe. Key breakthroughs came in the 1980s and 1990s, with advances in data analysis techniques. Signal extraction became possible through methods like matched filtering, which compares observational data against theoretical waveforms predicted by numerical simulations. These simulations, powered by the burgeoning field of computational astrophysics, allowed researchers to model gravitational waves from events like binary black hole mergers and neutron-star collisions. By identifying characteristic patterns in the noise, scientists could isolate gravitational wave signals with increasing confidence. The transition from theory to observation was marked by the establishment of international collaborations, such as LIGO in the United States, Virgo in Europe, and later, Kagra in Japan. These observatories pooled resources and expertise, building ever more sophisticated detectors. LIGO's two facilities, located in Hanford, Washington and Livingston, Louisiana, became operational in the late 1990s, but it wasn't until the advanced LIGO upgrade in 2015 that they achieved the sensitivity needed for detection. Groundbreaking discoveries began with the detection of gravitational waves from a binary black hole merger on September 14, 2015, an event designated GGW 150914. This observation not only confirmed Einstein's century-old prediction, but also validated decades of technological and scientific effort. Virgo soon joined the detection effort, and together these observatories began identifying a variety of gravitational wave sources, from additional black hole mergers to neutron-star collisions. These detections reshaped observational astronomy by providing a new way to study phenomena invisible to traditional electromagnetic telescopes. The success of gravitational wave detection owes much to advances in technology. Vacuum isolation systems, for instance, have been critical in reducing noise caused by air molecules interacting with the laser beams in interferometers. These systems create ultra-high vacuum environments that minimize disturbances, allowing for unprecedented sensitivity. Similarly, the use of advanced materials, such as fused silica for mirrors and suspensions, has helped minimize thermal noise, which arises from random molecular motion. These innovations represent the culmination of decades of research in material science and engineering. funding has played a pivotal role in the development of gravitational wave observatories. Early efforts relied heavily on government support from agencies like the National Science Foundation, NSF, in the United States and the European Research Council. Private philanthropy also contributed, with organizations such as the Kavli Foundation supporting research initiatives. These investments have yielded significant returns, not only in scientific knowledge but also in technological spin-offs, such as advancements in precision measurement and data processing. Theoretical efforts have paralleled experimental progress. The Einstein telescope, a proposed next-generation gravitational wave observatory, builds on lessons learned from LIGO and Virgo. Its innovative triangular design aims to enhance sensitivity to both high and low-frequency waves, expanding the range of detectable sources. Such projects highlight the forward-looking nature of gravitational wave research, which continues to push the boundaries of what is possible. Gravitational wave detection has also had a profound cultural impact, influencing everything from public understanding of science to the awarding of prestigious prizes. The 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for their contributions to LIGO and gravitational wave discovery. This recognition underscored the collaborative and interdisciplinary nature of the field, which brings together physicists, engineers, and astronomers in pursuit of a common goal. Numerical simulations have been a cornerstone of gravitational wave research, enabling predictions of waveforms for complex astrophysical events. These simulations require immense computational power, often running on supercomputers for weeks, to model scenarios like black hole mergers or neutron-star collisions. The insights gained from these simulations have been critical in interpreting observational data, bridging the gap between theory and experiment. As the field matures, the focus has expanded to include the development of even more sensitive detectors. Innovations like quantum squeezing, which reduces quantum noise in laser interferometry, promise to enhance sensitivity further. Other efforts aim to extend detection capabilities into space, with projects like the Laser Interferometer Space Antenna, LISA, targeting lower-frequency gravitational waves generated by supermassive black hole mergers and other cosmic phenomena. The history of gravitational wave detection is a testament to human ingenuity and perseverance. From the rudimentary Weber bars of the 1960s to the cutting-edge interferometers of today, this journey has been marked by both setbacks and triumphs. Each milestone has brought us closer to understanding the universe's most violent and mysterious events, demonstrating the transformative power of science to reveal the unseen. Pulsar timing arrays and the gravitational wave background. Pulsar timing arrays, PTAs, represent a groundbreaking approach to detecting gravitational waves, offering a complementary perspective to interferometer-based observatories like LIGO and Virgo. By harnessing the precise timing of pulsar emissions, PTAs target gravitational waves in the nanohertz frequency range, produced by cosmic phenomena such as supermassive black hole binaries. This section delves into the principles, techniques, challenges, and future of PTAs in the hunt for the gravitational wave background, GWB. Supernova remnants known as pulse-rodded stellar objects, pulsars, are the most accurate cosmic clocks in the universe. Exceptionally regularity is observed in the passage of radio waves emitted by these neutron stars as they spin at high speeds past Earth. Because of their extremely stable timing, millisecond pulsars, a subgroup of pulsars that spin hundreds of times per second, are ideal for detecting gravitational waves. Pulsars can change the distances between Earth and themselves by causing small stretching and compressing of spacetime, which can be detected by variations in the arrival timings of their pulses. Timing pulsar signals with nanosecond precision is an immense technical challenge. Astronomers employ sophisticated radio telescopes to capture pulsar emissions and use highly accurate atomic clocks to timestamp the arrival of these signals. Observations over months, years, or even decades are necessary to build datasets robust enough to identify the subtle effects of gravitational waves. The timing process must account for myriad factors, including the pulsar's rotational dynamics, its motion relative to Earth, and variations caused by the interstellar medium. Gravitational waves with durations of years to decades can be detected using pulsar timing arrays in the nanohertz frequency range. Detectors on the ground, such as LIGO, are only able to pick up somewhat higher frequencies, meaning they cannot reach this particular frequency region. Celestial phenomena such as galaxy mergers, supermassive black hole binaries, and other large-scale cosmic events that span vast amounts of time usually produce gravitational waves in the PTA range. It is possible for PTAs to deduce the existence of these low-frequency waves by seeing small, correlated temporal delays across several pulsars. Collaborations like NanoGrav, North American Nanohertz Observatory for Gravitational Waves, EPITER, European Pulsar Timing Array, and PPTA, Parkes Pulsar Timing Array, lead global efforts in this field. These groups pool data from radio observatories worldwide, enabling the high-precision timing and statistical analyses required to detect gravitational wave signals. Their efforts recently culminated in compelling evidence for a GWB, a major milestone in astrophysics. Signal processing techniques are central to identifying GWB patterns in pulsar timing data. Scientists use cross-correlation methods to compare timing residuals, deviations from expected pulse arrival times, across multiple pulsars. Gravitational waves produce a distinct pattern of correlated residuals, known as the Helling-Downs curve, which depends on the angular separation between pulsar pairs. Identifying this pattern amid timing noise and other astrophysical signals is the crux of PTA science. Individual pulsars contribute valuable data, but PTAs rely on observing arrays of pulsars to detect the GWB. Each pulsar provides a unique baseline to measure spacetime distortions, and combining data from multiple pulsars increases sensitivity and reduces uncertainties. A well-distributed array of millisecond pulsars across the sky enables astronomers to map the gravitational wave signals with greater precision, much like a geodetic network measuring Earth's shape. Dispersion measures, which quantify the delay in pulse arrival times caused by the interstellar medium, are critical for accurate pulsar timing. Free electrons in interstellar space slow down radio waves, introducing frequency-dependent delays. Correcting for these effects requires monitoring variations in dispersion measures over time, ensuring that any residual timing anomalies are not mistaken for gravitational wave signatures. Data cross-correlation between pulsars is essential for detecting the GWB. By analyzing timing residuals across dozens of pulsars, astronomers look for the spatial correlations predicted by the Helling-Downs curve. This statistical approach strengthens the case for a gravitational wave origin, distinguishing it from uncorrelated noise or intrinsic pulsar timing variations. Despite the potential it has, PTA research is confronted with formidable obstacles. It is a difficult effort to isolate GWB signals from inherent pulsar timing noise, which might be generated by rotating abnormalities or magnetic field instabilities. Errors in accounting for clock and telescope delays, as well as inaccurate modeling of the solar system's barycenter, the point at which gravitational wave-induced temporal changes are observed, are additional sources of noise. PTA detections complement the findings of ground-based observatories like LIGO and Virgo, bridging the gap between different gravitational wave frequency ranges. While PTAs probe the nanohertz domain, LIGO and Virgo focus on kilohertz frequencies, allowing researchers to study gravitational waves from both long time-scale cosmic events and shorter duration phenomena like neutron star mergers. Together, these methods offer a more comprehensive view of the gravitational wave spectrum. The next decade holds tremendous promise for PTAs. Improved telescope sensitivity, expanded pulsar arrays, and advancements in data analysis techniques are expected to enhance detection capabilities. Projects like the Square Kilometre Array, SKA, which will vastly increase the number of detectable pulsars, could revolutionize PTA science, enabling detailed studies of the GWB and even pinpointing individual gravitational wave sources. Key pulsars play a disproportionate role in PTA efforts, with some contributing more reliable and precise timing data than others. Pulsars like J1713 plus 0747 and J04374715 are critical for current GWB detection efforts due to their exceptional stability and proximity to Earth. These golden pulsars form the backbone of PTA datasets, providing high-quality baselines for gravitational wave searches. Magnetic field irregularities in pulsars introduce another layer of complexity. Variations in the pulsar's magnetic field can affect its rotational stability, introducing noise into timing measurements. Understanding and modeling these effects are crucial for achieving the precision needed to detect gravitational waves. Statistical frameworks underpin the interpretation of PTA signals. Bayesian inference, for example, allows researchers to assess the probability of a gravitational wave signal given the observed data, accounting for uncertainties and competing hypotheses. These rigorous statistical methods ensure that PTA detections are robust and scientifically credible. The study of pulsar timing arrays has opened a new frontier in gravitational wave astronomy, providing a window into the universe's largest and most distant structures. By leveraging the natural precision of pulsars and the collaborative efforts of international observatories, PTAs have not only demonstrated the existence of the GWB, but also set the stage for even more profound discoveries in the years to come. Individual gravitational wave events. Gravitational wave astronomy took a dramatic leap forward with the detection of individual gravitational wave events, beginning with GW 150914, the first ever observation of a black hole merger. These discrete events not only confirm the existence of gravitational waves, but also provide critical insights into the origins and characteristics of the gravitational wave background, GWB. The GWB is thought to be a cumulative signal, an ocean of ripples in spacetime generated by countless individual wave-producing phenomena across cosmic history. Understanding the GWB requires unraveling the contribution of these individual events, each offering a unique piece of the puzzle. The landmark GW 150914 detection in 2015 by LIGO marked the first direct observation of gravitational waves caused by the merger of two stellar mass black holes. This event, which released energy equivalent to 3 solar masses in the form of gravitational waves, provided the first concrete evidence of black hole mergers as significant contributors to the GWB. The nearly chirp-like signal observed, characterized by increasing frequency and amplitude, has since become a template for identifying similar events. Each black hole merger contributes a distinct waveform to the GWB, with properties determined by the masses, spins, and orbital dynamics of the merging bodies. Binary neutron star mergers also play a critical role in shaping the GWB, albeit with different characteristics than black hole mergers. These events, such as the famous GW 170817 detection, emit gravitational waves at slightly lower frequencies and are accompanied by electromagnetic counterparts like gamma-ray bursts. The kilonova produced in such mergers, a luminous explosion powered by the radioactive decay of heavy elements, provides a wealth of multi-messenger data linking gravitational wave signals to astrophysical phenomena. The GWB accumulates signals from billions of such events, weaving them into a stochastic background. Eccentric binary systems, where compact objects follow elliptical orbits, add further complexity to the GWB. Unlike circular binaries, eccentric systems produce gravitational waves across a broader range of frequencies, with bursts of energy released at periastron, the closest approach in their orbits. These bursts create distinctive waveforms that, when aggregated, contribute a unique spectral signature to the GWB. Eccentric binaries are particularly common in dense stellar environments, like globular clusters, where gravitational interactions perturb otherwise circular orbits. When gravitational waves are correlated with electromagnetic signals, multi-messenger astronomy completely changes our view of wave-producing processes. One example is the gamma-ray burst that was discovered with GW 170817. This burst revealed details on the neutron star merger's geometry and the debris it produced. These associations provide further context for the GWB interpretation and provide credence to the idea that gravitational wave episodes have astrophysical causes. Kilonovae, which are radioactive remnants of neutron star mergers, also play an important role in elucidating the heavy elements produced during these catastrophic explosions. The differences in wave signatures between neutron star and black hole mergers are critical for disentangling their contributions to the GWB. Black hole mergers typically produce higher frequency waves with no accompanying electromagnetic emission, while neutron star mergers emit waves at slightly lower frequencies, often accompanied by rich electromagnetic signals. These distinctions allow astrophysicists to model the relative contributions of each type of merger to the GWB, enhancing the understanding of its composite nature. An intriguing feature to the GWB are hierarchical mergers, in which black holes generated from earlier mergers converge again. Waveforms with increased mass and energy are produced by second-generation mergers, which often take place in dense star settings, such as galactic cores. Throughout cosmic history, the GWB has been enhanced by hierarchical mergers with unique high-frequency components, providing insight into the gradual development of gravitational wave sources. Modeling the GWB requires sophisticated techniques to account for the superposition of waveforms from countless events. Each individual gravitational wave signal combines with others, creating an overlapping stochastic pattern. Numerical simulations play a pivotal role in predicting the spectral shape of the GWB, factoring in the merger rates, mass distributions, and orbital dynamics of compact object binaries. These models help differentiate the GWB from other noise sources in observational data. Rare and extreme events, such as hypermassive black hole collisions, provide unique contributions to the GWB. These events, involving black holes with masses exceeding 100 solar masses, produce gravitational waves of exceptional amplitude and duration. Though rare, their signals leave indelible marks on the GWB, potentially dominating specific frequency bands. Detecting such events offers insights into the formation of massive black holes and their role in cosmic structure formation. Population synthesis studies, which model the demographics of gravitational wave sources, are invaluable for understanding the GWB. These studies simulate billions of binary systems, incorporating factors like stellar evolution, initial mass functions, and environmental influences. By comparing these synthetic populations to observed data, researchers can refine predictions about the frequency and amplitude of the GWB, as well as the relative contributions of different source classes. The evolution of merger rates throughout cosmic time determines the shape of the GWB. A greater population of wave-producing binaries resulted from the early universe's higher star formation and black hole generation rates. These rates decreased with cosmic aging, changing the GWB's amplitude and frequency distribution. The interpretation of the GWB as a record of cosmic history relies on comprehending its temporal progression. The GWB also provides indirect evidence for intermediate mass black holes, IMBHs, objects with masses between 100 and 100,000 solar masses. These elusive black holes, which may form through the mergers of stellar mass black holes, contribute gravitational waves at intermediate frequencies. Detecting their imprint in the GWB could resolve long-standing questions about their existence and role in galaxy formation. Galactic centers play a significant role in amplifying the GWB signals due to their high-density environments. Supermassive black holes at galactic cores can interact with surrounding stars and compact objects, forming binaries or capturing other black holes. These interactions result in frequent and energetic mergers, contributing prominently to the GWB. Studying these environments helps link the GWB to the dynamics of galactic evolution. Despite advancements, current detectors have limitations in resolving faint individual events within the GWB. The stochastic nature of the background, combined with detector noise, makes it challenging to distinguish weaker signals. However, improvements in detector sensitivity and the development of next-generation observatories, such as the Einstein telescope and LISA, promise to unveil more detailed structures within the GWB. Theoretical predictions for exotic merger events, such as collisions involving boson stars or other hypothetical compact objects, add speculative but intriguing dimensions to the GWB. These exotic events, if they exist, would produce distinctive waveforms, unlike those from black holes or neutron stars. Detecting such signals would expand the understanding of fundamental physics and the nature of compact objects. The gravitational wave background is not merely a cacophony of indistinct signals, but a richly layered symphony of cosmic events. From black hole mergers to neutron-star collisions and beyond, each event contributes its unique frequency, amplitude, and duration to this universal hum. By decoding these signals, astrophysicists are piecing together the story of the universe's most violent and transformative moments, revealing the interconnectedness of cosmic phenomena. Challenges in detecting the gravitational wave background. Detecting the gravitational wave background, GWB, is one of the most ambitious and intricate challenges in modern astrophysics. Unlike individual gravitational wave signals, the GWB is a diffuse and stochastic hum arising from countless overlapping sources across cosmic history. The nature of this background signal presents a range of obstacles, from technical limitations in instrumentation to the complexities of data analysis. Understanding these challenges is critical to advancing our ability to detect and interpret the GWB, ultimately unraveling the secrets of the universe. The sensitivity of current interferometers, such as LIGO, Virgo, and CAGRA, represents a significant limitation in detecting the faint signals of the GWB. While these detectors are capable of identifying discrete events like black hole mergers, their ability to distinguish the subtle, continuous background signal is constrained by noise levels and their intrinsic design. Achieving the sensitivity required to detect the GWB demands cutting-edge technology and enhancements in detector infrastructure. Background noise is a persistent challenge, particularly from seismic and thermal vibrations. Ground-based observatories are constantly affected by the movement of the Earth, from tectonic activity to the vibrations caused by nearby human activity. Even minor disturbances can introduce noise that masks the faint signals of the GWB. Advanced isolation systems and vibration damping technologies are employed to mitigate these effects, but achieving complete isolation remains elusive. Atmospheric disturbances, such as fluctuations in temperature and air pressure, also impact ground-based observatories. Variations in refractive indices can alter the path of laser beams within the interferometers, introducing noise into the data. While vacuum systems protect critical components, external atmospheric effects can still propagate into the system through infrastructure, requiring precise environmental monitoring and control. Laser noise is another critical factor in interferometry. Even the most stable lasers experience minute fluctuations in frequency and intensity, which can mimic or obscure gravitational wave signals. Efforts to mitigate laser noise include the use of ultra-stable laser systems, advanced feedback mechanisms, and improved mirror coatings to reduce optical imperfections. Separating stochastic signals from astrophysical noise is a major obstacle. Because of its intrinsic diffuse nature, the GWB mixes with other sources of gravitational waves, including galaxy binaries and other astronomical events in the background. Sophisticated modeling, statistical methodologies, and extended observational baselines are needed to distinguish the GWB from these foreground sources and to uncover persistent trends that indicate a background signal. Interference from terrestrial radio frequency sources also poses a problem, particularly for observatories using radio-based methods like pulsar timing arrays, PTAs. Signals from communication satellites, television broadcasts, and other human-made sources can contaminate the data, necessitating stringent filtering techniques and carefully chosen observatory locations far from urban centers. Gravitational noise from Earth's own mass fluctuations, such as those caused by atmospheric pressure changes, ocean tides, and subsurface movements, adds another layer of complexity. These fluctuations create minute variations in local gravitational fields, introducing additional noise into the data. Addressing this requires advanced modeling to predict and subtract these terrestrial contributions. The computational challenges of analyzing stochastic signals are immense. Unlike discrete gravitational wave events with clear waveforms, the GWB requires the aggregation and statistical analysis of vast amounts of data over extended periods. Processing this data demands high-performance computing infrastructure and innovative algorithms capable of identifying subtle correlations amidst overwhelming noise. Another problem is isolating the GWB from sources in the foreground, including gravitational waves from galactic binaries. Continuous gravitational waves at frequencies that coincide with the GWB are emitted by these binaries, especially white dwarf pairings inside the Milky Way. A thorough spectrum analysis and the creation of templates for recognized foreground sources are required to detangle these signals. Calibration errors in observatory instrumentation further complicate GWB detection. Tiny deviations in the alignment of mirrors, laser frequencies, or detector sensitivities can introduce biases into the data. Regular calibration and cross-checking between observatories are essential to maintain data integrity and ensure that detected signals are genuine. Global collaboration is a necessity for GWB detection. The faint and stochastic nature of the GWB means that no single observatory is likely to achieve detection alone. Coordinated efforts across multiple observatories, such as LIGO, Virgo, CAGRA, and Pulsar timing collaborations like NanoGrav, are required to combine data and enhance sensitivity. However, achieving seamless collaboration across international teams poses logistical, technical, and funding challenges. Long observational baselines are critical for detecting the GWB. The longer the duration of observation, the greater the chances of identifying consistent patterns in the data indicative of a background signal. However, maintaining continuous observations over years or decades is resource-intensive and subject to interruptions from maintenance, upgrades, or unforeseen downtime. Detector downtime itself is a significant issue. Even short interruptions in data collection can create gaps that complicate the analysis of long-term signals. Planning for redundancy, minimizing downtime through efficient maintenance schedules, and ensuring rapid recovery from technical issues are all crucial for sustained observations. Building next-generation observatories to enhance sensitivity to the GWB requires significant resources. Projects like the Einstein Telescope and the Laser Interferometer Space Antenna, LISA, aim to overcome many of the current limitations, but their development and construction are constrained by funding, technological hurdles, and political considerations. The scale and complexity of these observatories demand international cooperation and long-term commitments. Improving detector sensitivity is a vital yet frightening task for the future. Achieving the GWB detection accuracy could necessitate quantum technology advancements, cryogenic noise reduction techniques, and very stable new materials. Investing much in research and development is necessary for these potential breakthroughs. The determination and resourcefulness of the human race are on full display in the search for the gravitational wave background. Every obstacle, from reducing background noise to fostering international cooperation, is an opportunity for groundbreaking research and development in science and technology. Redefining our view of the cosmos and uncovering the echoes of cosmic events that have molded its past. Overcoming these challenges will expose the mysteries of the GWB. Advanced theoretical models of the gravitational wave background. The gravitational wave background, GWB, is a cosmic symphony performed by the most mysterious and deep cosmic occurrences. It is not only a hum emanating from faraway astronomical sources. The GWB's origins and properties can be better understood with the use of sophisticated theoretical models, which in turn provide light on cosmology, basic physics, and perhaps undiscovered fields of physics. The stochastic gravitational wave spectrum is enriched by the distinct signatures of these models, which cover a wide spectrum of occurrences, from the inflationary era to quantum gravity effects. The concept of primordial gravitational waves from inflationary cosmology lies at the heart of many theoretical frameworks for the GWB. Inflation, a rapid exponential expansion of the universe fractions of a second after the Big Bang, stretched quantum fluctuations in spacetime to macroscopic scales. These fluctuations produced gravitational waves that, unlike electromagnetic radiation, permeated the universe almost unimpeded. The resulting stochastic background carries imprints of the inflationary potential, providing a unique window into the physics of the early universe. Detecting these primordial waves would validate key aspects of inflationary theory and constrain models of the energy scale at which inflation occurred. Phase transitions in the early universe are another significant source of stochastic gravitational waves. As the universe cooled, it underwent several transitions, such as the electroweak phase transition, where fundamental forces separated and the formation of the Higgs field. If these transitions were first order, they would have generated bubbles of true vacuum expanding and colliding, producing gravitational waves. The GWB from these events would carry information about the temperature, dynamics, and symmetries of the early universe, providing clues about particle physics at energy scales inaccessible to current accelerators. Cosmic string dynamics also contributes to theoretical models of the GWB. Cosmic strings, hypothesized one-dimensional topological defects formed during symmetry-breaking phase transitions, would generate bursts of gravitational waves as they interact, oscillate, and reconnect. These waves accumulate over time, forming a stochastic background. Observing such signals would support theories of high-energy physics that predict the existence of cosmic strings, such as certain grand unified theories or string theory scenarios. Gravitational wave generation relies heavily on scalar field dynamics, particularly in early universe models. Gravitational waves can be produced by oscillations, instabilities, or interactions with other fields by scalar fields, which are the basis of ideas such as inflation and some dark energy models. These processes leave unique spectral fingerprints on the GWB, which may provide an observational window into the nature and function of scalar fields in the universe. Modifications of general relativity, GR, are another area of interest in advanced GWB models. Extensions or alternatives to GR, such as FR, gravity or scalar tensor theories, predict different gravitational wave dispersion relations and polarization modes. These modifications affect the amplitude, frequency spectrum, and angular distribution of the GWB, allowing tests of GR in regimes where traditional observational methods fall short. Detecting deviations in the GWB could signal the need for a new theoretical framework to describe gravity. Axion-like particles, candidates for dark matter, may also contribute to the GWB spectra. Interactions between axions and electromagnetic or gravitational fields can produce distinct signatures in the stochastic background. For instance, oscillations in the axion field during the early universe could resonate with gravitational waves, creating amplified or suppressed features in specific frequency bands. Such signals would offer indirect evidence for these elusive particles and their role in cosmic evolution. Particle physics models, including supersymmetry, SUSY, predict unique contributions to the GWB. SUSY introduces a host of new particles and interactions, some of which could generate gravitational waves through phase transitions or annihilation processes. Additionally, the decay or annihilation of heavy relic particles in SUSY models could produce stochastic gravitational waves, adding complexity to the GWB spectrum. These signatures would provide a bridge between particle physics and cosmology. There are significant ramifications for the GWB from quantum gravity theories. String theory and loop quantum gravity are two methods that suggest quantum corrections to spacetime on the tiniest scales, which might change the way gravitational waves travel. These effects have the potential to imprint non-standard polarization modes or high-frequency modes on the GWB. A long-standing objective in theoretical physics is to test quantum gravity, and seeing such phenomena would give an experimental footing toward that end. Black hole evaporation via Hawking radiation may also contribute to the GWB. As black holes evaporate over cosmic timescales, they emit gravitational waves alongside other forms of radiation. In the early universe, primordial black holes, if they existed, could have evaporated en masse, leaving a faint gravitational wave signature in the stochastic background. This signal would serve as evidence for primordial black holes and their role in the universe's evolution. Extra dimensions, a staple of certain high-energy theories, have intriguing implications for the GWB. Models like those proposed in string theory or the Randall-Sundrum framework suggest that gravitational waves could interact with or propagate through extra dimensions, altering their observed properties. This interaction could create deviations in the GWB's spectrum, revealing the existence and characteristics of higher dimensional spaces. Anisotropies in the early universe could leave imprints on the GWB. Irregularities in the distribution of matter and energy during cosmic inflation or other epochs could introduce directional variations in gravitational wave intensity. These anisotropies would provide a unique map of the universe's structure at its earliest stages, complementing observations of the cosmic microwave background. Non-standard cosmological models, such as bouncing cosmologies or cyclic universes, predict unique GWB signatures. For example, in a bouncing universe where the Big Bang is preceded by a contraction phase, the dynamics of the bounce could generate gravitational waves with distinct spectral features. Observing these patterns would challenge the conventional inflationary paradigm and offer alternatives to standard cosmological narratives. Gravitational wave echoes from exotic compact objects, ECOs, such as boson stars or gravastars, also contribute to advanced GWB models. These objects, hypothesized as alternatives to black holes, produce unique waveforms due to their structure and interactions. If such echoes are detected in the GWB, they could signal the existence of new astrophysical phenomena beyond traditional compact objects. Dark matter dynamics interplay intriguingly with the GWB. Clumps or streams of dark matter interacting with gravitational wave sources could modulate the background's intensity and frequency. Additionally, certain dark matter models predict gravitational wave production during particle annihilation or decay. These interactions would enrich our understanding of dark matter's properties and distribution. The GWB provides a powerful tool for testing theories of cosmic inflation. By comparing the observed spectrum to theoretical predictions, scientists can constrain the inflationary potential, the number of E-foldings, and the energy scale of inflation. This analysis bridges cosmology and fundamental physics, offering a direct glimpse into the universe's earliest moments. Advanced theoretical models of the GWB represent a vibrant frontier in astrophysics and cosmology. Each model offers a piece of the puzzle, connecting gravitational waves to the deepest mysteries of the universe, from the nature of spacetime to the dynamics of fundamental particles. Future detection technologies for the GWB. Gravitational wave research is poised for transformative breakthroughs, with advanced detection technologies at the forefront of these efforts. As we seek to unravel the intricate mysteries encoded in the gravitational wave background, GWB, innovative approaches are reshaping the field, pushing the boundaries of sensitivity, precision, and scope. These future technologies will not only refine our understanding of the universe, but also open new windows into phenomena we have yet to imagine. Space-based observatories like the Laser Interferometer Space Antenna, LISA, represent a monumental leap in gravitational wave detection. Scheduled for launch in the 2030s, LISA will operate with 3 spacecraft forming a triangular constellation separated by millions of kilometers. This configuration allows it to detect low-frequency gravitational waves that are inaccessible to ground-based detectors, such as those generated by supermassive black hole mergers or cosmic strings. LISA's ability to operate outside Earth's noise-rich environment will provide unprecedented sensitivity to the faintest ripples in spacetime. Complementing LISA, the proposed Big Bang Observer and DeCIGO, Decihertz Interferometer Gravitational Wave Observatory, aim to explore even finer aspects of the GWB, offering insights into primordial waves from the early universe. These missions will enhance our ability to probe the inflationary epoch, potentially uncovering the fingerprints of cosmic expansion. On Earth, the next-generation Einstein telescope, ET, is set to redefine the sensitivity of ground-based interferometers. With its triangular design and underground location, the ET will minimize seismic noise and thermal fluctuations, allowing for improved detection of low-frequency gravitational waves. Its advanced cryogenic mirrors will further reduce thermal noise, enabling the exploration of faint and distant sources that current detectors like LIGO and Virgo cannot reach. Ground-based interferometers will also play a pivotal role in extending the frequency range of GWB detection. The Cosmic Explorer, with arms stretching up to 40 kilometers, promises to capture gravitational waves from stellar mass binaries and other astrophysical sources with unparalleled clarity. These observatories will work in tandem with space-based detectors, creating a multi-band network that spans the gravitational wave spectrum. Emerging technologies like atom interferometry are introducing novel methods for gravitational wave detection. By manipulating ultra-cold atoms with laser pulses, these systems measure minute distortions in spacetime with extraordinary precision. Atom interferometers are particularly promising for detecting ultra-low frequency gravitational waves, which are critical for studying phenomena such as dark matter interactions and cosmic inflation. Quantum technologies are also revolutionizing sensitivity in gravitational wave detectors. Squeezed light states, which reduce quantum noise, have already enhanced the performance of LIGO and Virgo. Future detectors will build on this foundation, incorporating quantum metrology techniques to further suppress noise and improve signal clarity. Thermal noise remains a significant challenge in gravitational wave detection, but cryogenic cooling offers a solution. By operating mirrors and other critical components at near absolute zero temperatures, cryogenic technologies reduce atomic vibrations that interfere with measurements. The Einstein telescope will be among the first to employ this technique on a large scale, setting a new standard for detector sensitivity. Equally important are kilometer-scale vacuum chambers, which provide the ultra-clean environments necessary for precise interferometry. Advances in vacuum technology will allow detectors to maintain their performance over extended observational periods, minimizing the impact of environmental noise. Next-generation pulsar timing arrays, PTAs, are another cornerstone of future GWB research. By monitoring the timing of millisecond pulsars, highly stable cosmic clocks, these arrays detect nanohertz frequency gravitational waves. Efforts to expand sky coverage and incorporate more pulsars into the network will increase the sensitivity and resolution of PTA data, enabling the identification of GWB signals from supermassive black hole binaries and other sources. Collaborations like NanoGrav, North American Nanohertz Observatory for Gravitational Waves, EPTA, European Pulsar Timing Array, and PPTA, Parkes Pulsar Timing Array, are leading this charge with plans to integrate their datasets into a global PTA network. This collective approach will provide a comprehensive view of the GWB across the sky. The increasing complexity of gravitational wave data demands advanced analytical tools, and artificial intelligence, AI algorithms, are stepping up to the challenge. Machine learning techniques are being developed to filter noise, identify patterns, and extract weak stochastic signals from massive datasets. These algorithms can adapt to evolving detector configurations, ensuring optimal performance as new technologies come online. AI will also enhance cross-correlation methods, which compare data from multiple detectors to isolate GWB signals. This technique is crucial for distinguishing stochastic waves from local noise and other astrophysical foregrounds. The phenomenon of gravitational wave memory, a permanent distortion in spacetime caused by certain wave events, offers a new avenue for GWB research. Future detectors will be designed to identify these subtle imprints, providing insights into the most energetic cosmic events, such as black hole mergers and supernova explosions. Multiband detection strategies will play a pivotal role in capturing the full spectrum of GWB sources. By coordinating observations across space-based and ground-based detectors, scientists can piece together a more complete picture of the gravitational wave universe, linking events across different frequency ranges. Looking further ahead, the Moon offers a unique platform for gravitational wave detection. Lunar-based interferometers could operate free from the seismic and atmospheric disturbances that plague Earth-based observatories. The Moon's stable environment and low gravity would enable the construction of ultra-sensitive detectors, potentially capable of capturing the faintest GWB signals. Even more ambitious are theoretical concepts for cosmic-scale gravitational wave detectors, which envision utilizing astronomical distances, measured in light-years, as baselines for interferometry. While currently speculative, these ideas could one day unlock entirely new dimensions of gravitational wave research. The future of GWB research is defined by its innovative technologies and interdisciplinary collaborations. As space-based detectors like LISA and ground-based observatories like the Einstein telescope come online, they will work alongside emerging tools like atom interferometers and AI-driven analytics to push the boundaries of discovery. These advancements promise not only to refine our understanding of the GWB, but also to transform our knowledge of the universe, unveiling its deepest secrets and most profound truths. Synergies between gravitational wave background and cosmic signals. The study of the gravitational wave background, GWB, is not isolated from other branches of astrophysics and cosmology. Instead, it thrives at the intersection of multiple cosmic signals, leveraging insights from electromagnetic waves, neutrinos, cosmic rays, and more. By integrating these diverse observations, scientists are piecing together a more comprehensive narrative of the universe's evolution, bridging gaps between theoretical models and empirical data. The synergies between the GWB and other cosmic signals underscore the richness of multi-messenger astronomy. Gravitational waves and electromagnetic signals are pillars of multi-messenger astronomy, complementing each other in unique ways. While gravitational waves reveal the motion and dynamics of massive objects like black holes and neutron stars, electromagnetic signals provide information about the accompanying energetic processes. For instance, the simultaneous detection of a gravitational wave from a binary neutron-star merger and a gamma-ray burst, GRB, in 2017, GW170817, marked a watershed moment. This event demonstrated how the gravitational wave signal provided precise data about the merger dynamics, while the electromagnetic counterpart offered insights into the kilonova explosion, the surrounding environment, and heavy element synthesis. Such correlations deepen our understanding of the physics driving cosmic events. Neutrino observatories, such as IceCube in Antarctica, play a vital role in complementing GWB studies. Neutrinos, nearly massless particles, are produced in vast quantities during catastrophic astrophysical events like supernovae or black hole formation. These particles can travel unimpeded across vast distances, making them invaluable probes of high-energy processes. When a gravitational wave event is detected, scientists can cross-reference neutrino data to locate and characterize the event's source. This dual detection not only corroborates the gravitational wave signal, but also sheds light on the physics of extreme matter and energy environments. High-energy cosmic rays, the most energetic particles in the universe, offer another avenue for synergy with gravitational wave signals. Cosmic rays are often linked to the same energetic processes that produce gravitational waves, such as neutron-star collisions or the accretion disks of active galactic nuclei, AGN. By identifying patterns in cosmic ray arrival directions and correlating them with gravitational wave detections, researchers can better understand the acceleration mechanisms behind these particles and their relationship to cosmic-scale phenomena. Fast radio bursts, FRBs, transient bursts of radio waves lasting only milliseconds, have recently been suggested as potential counterparts to gravitational wave events. Some theories propose that these enigmatic bursts may arise from neutron star mergers or magnetar flares, both scenarios that could produce gravitational waves. By cross-referencing FRB detections with gravitational wave data, scientists hope to identify whether these phenomena are causally linked, thereby unlocking the mysteries behind FRB origins. Validating GWB models has been greatly aided by gamma-ray bursts, GRBs, which have long been linked to the catastrophic collapse of large stars or the merging of compact objects. Theoretical predictions regarding the gravitational wave emissions that precede GRBs may be confirmed by analyzing their timing, duration, and energy characteristics. For example, the GWB spectral predictions can be impacted by the energy produced in the burst, which can limit the mass and spin of the merger leftovers. Quasars, the luminous cores of active galaxies powered by supermassive black holes, serve as indirect indicators of GWB contributions. Their variability and emission spectra often point to dynamic processes in their surrounding accretion disks. Gravitational waves from merging supermassive black holes in quasar-hosting galaxies contribute to the low-frequency GWB. Studying quasar distributions and dynamics offers indirect insights into the cosmic history of black hole mergers. Magnetars, highly magnetized neutron stars, are thought to be significant contributors to certain gravitational wave signals. Their immense magnetic fields occasionally undergo sudden reconfigurations, releasing energy in the form of giant flares and gravitational waves. These events are rare, but can leave distinct imprints on the GWB spectrum. Understanding the interplay between magnetic field dynamics and spacetime ripples enriches models of compact object behavior. Gravitational lensing, a phenomenon where massive objects bend and magnify gravitational waves, provides a unique angle on GWB studies. Lensing effects can distort or amplify gravitational wave signals, introducing variations that must be accounted for in background analysis. Additionally, the observation of lensed gravitational waves offers an opportunity to map the distribution of matter in the universe, linking GWB studies to large-scale structure research. The study of galactic baryonic oscillations, the effects of primordial sound waves on the distribution of matter, also has some overlap with GWB studies. The GWB anisotropies are shaped by galaxy clustering, which is in turn affected by these oscillations. Researchers may test predictions about the expansion and distribution of matter in the universe, as well as improve cosmological models by cross-correlating this data. Dark energy and cosmic acceleration, two of the most profound mysteries in modern cosmology, also interact with GWB studies. Gravitational waves propagate through the expanding universe, and their energy distribution can be subtly affected by the presence of dark energy. By analyzing these effects, scientists aim to constrain models of dark energy and explore its role in the evolution of cosmic structures. Cosmic voids, vast regions of space with few galaxies, provide a unique testing ground for gravitational wave propagation. These underdense areas influence how gravitational waves travel, altering their amplitude and phase. Studying the correlations between voids and gravitational wave signals helps refine models of large-scale cosmic dynamics and the distribution of matter. Galaxy clustering introduces anisotropies into the GWB. The spatial arrangement of galaxies and their interactions contribute to the gravitational wave signals emanating from binary mergers within galactic environments. These clustering patterns, when studied alongside the GWB, offer a richer picture of how cosmic structures influence wave production and propagation. Transient electromagnetic counterparts, such as supernovae, kilonovae, and jets, provide critical contextual information for gravitational wave events. The timing and characteristics of these counterparts help pinpoint the origin and nature of the events, making it possible to study the environments where gravitational waves are produced. This multi-messenger approach enhances the resolution and reliability of GWB studies. Dust and plasma, often considered noise in astrophysical observations, can interact with gravitational waves, subtly altering their signatures. These interactions, though weak, provide valuable insights into the interstellar and intergalactic medium. By accounting for these effects, researchers can refine their models of wave propagation and improve the precision of GWB measurements. Interdisciplinary studies linking GWB research with particle physics open new avenues for understanding fundamental forces and particles. For example, gravitational wave observations might offer indirect evidence for axions, dark matter interactions, or quantum gravity effects. By uniting the insights from these fields, scientists are constructing a more holistic understanding of the universe. The synergies between the GWB and other cosmic signals underscore the interconnected nature of the universe's phenomena. By integrating gravitational wave data with electromagnetic, neutrino, and cosmic ray observations, researchers are unlocking a more complete picture of cosmic evolution. Philosophical implications of detecting the GWB. The finding of the gravitational wave background, GWB, goes beyond the realms of astronomy and physics and prompts deep philosophical contemplation. It completely changes how we think about the universe and how we fit within it, by shedding light on its beginnings and material composition. Scientists are piecing together a story of creation and interdependence by picking up on the faint echoes of the oldest cosmic events, which questions long-held beliefs. The GWB provides a direct glimpse into the earliest moments of the universe, making it a powerful tool for probing the origins of existence. By detecting waves generated during processes like cosmic inflation or early phase transitions, humanity gains access to a cosmic memory that predates the formation of stars and galaxies. These observations challenge us to reconsider what it means to understand origins, not as isolated events, but as intricate unfolding processes written into the very fabric of space-time. Human perception is inherently bound by timescales familiar to our daily lives, but the GWB operates on scales spanning billions of years. This temporal vastness challenges our ability to comprehend the universe, pushing us to adopt perspectives that extend far beyond our immediate experiences. The notion that a single signal might carry information from epochs before Earth existed invites reflection on our fleeting presence in the cosmic timeline. The concept of the GWB introduces the idea of cosmic noise, a symphony of waves generated by countless overlapping events. Far from being chaotic, this noise embodies a form of universal harmony, a testament to the interconnectedness of all astrophysical phenomena. Philosophically, it aligns with ancient ideas about the music of the spheres, suggesting that even the most violent cosmic events contribute to a larger, unified narrative of balance and structure. Detecting the GWB also challenges anthropocentric views of the universe. Gravitational waves operate independently of human perception, interacting with space-time on a fundamental level that exists regardless of observation. Their discovery serves as a humbling reminder that humanity occupies a small niche within a vast, intricate cosmos. This shift in perspective echoes the Copernican revolution, expanding our awareness of the universe's complexity. Gravitational waves have been described as the heartbeat of the cosmos, carrying the rhythms of black hole mergers, neutron star collisions, and early cosmic processes. This poetic framing emphasizes the dynamism and vitality of the universe, inviting a view of spacetime not as static, but as alive with motion and energy. This metaphor enriches our understanding of the universe as an interconnected, evolving entity. The pursuit of the GWB raises ethical questions about resource allocation for fundamental research. The enormous investments in observatories like LIGO and Virgo, as well as in next-generation projects, prompt debates about the balance between scientific advancement and addressing immediate human needs. However, the philosophical argument for such research lies in its capacity to inspire, unify, and expand humanity's collective knowledge, fostering a sense of purpose beyond material concerns. The GWB expands the scope of cosmological inquiry, allowing humanity to ask questions about events and phenomena that were previously inaccessible. It transforms theoretical musings about the early universe into testable hypotheses, bridging the gap between philosophy and empirical science. This expansion underscores the importance of curiosity as a driving force in human progress. Gravitational waves occupy a unique space where science and metaphysics intersect. They prompt questions about the nature of reality, the interconnectedness of all things, and the mechanisms underlying existence itself. By detecting the ripples of events billions of years old, humanity is engaging with the very structure of reality in a way that blurs the lines between empirical inquiry and deeper existential reflection. The discovery of gravitational waves has inspired cultural interpretations across the globe, reflecting diverse ways of understanding and relating to the cosmos. In some traditions, these waves might be seen as echoes of creation, aligning with spiritual narratives about the origins and continuity of existence. By fostering cross-cultural dialogue, the GWB enriches not only scientific understanding, but also humanity's collective imagination. As gravitational wave data reveals insights into spacetime, matter, and energy, it informs efforts to reconcile general relativity and quantum mechanics. Philosophically, this quest mirrors humanity's perennial search for unity and coherence, reflecting a deep-seated desire to understand the universe as a singular, interconnected whole. The potential connection between the GWB and the multiverse hypothesis opens new dimensions for philosophical exploration. If gravitational waves carry imprints of interactions between multiple universes, they could offer the first empirical evidence for a reality beyond our own. This possibility invites speculation about the nature of existence and humanity's place within a potentially infinite cosmos. The detection of gravitational waves also challenges traditional notions of causality. Events separated by billions of years are now observed as overlapping influences on the GWB, blurring the line between cause and effect. This shift invites re-evaluation of how we understand time, sequence, and the interplay of events on cosmic scales. The metaphor of the music of the spheres, rooted in ancient philosophy, is redefined in light of gravitational wave discoveries. The GWB becomes a literal expression of this music, with each wave representing a note in the cosmic symphony. This modern reinterpretation bridges ancient and contemporary views, underscoring the enduring human fascination with the universe's harmonies. To promote international cooperation and harmony, the GWB is an invaluable resource. The fact that scientists, engineers, and institutions from all over the globe are working together to find it is a testament to how far we can go as a species in our quest for understanding. Collaboration is essential to comprehending and prospering in the universe, and this cooperative mentality reflects that interconnection. The philosophical implications of the GWB challenge humanity to think beyond immediate tangible realities, inviting profound reflection on time, causality, and existence. As a bridge between science and philosophy, the GWB enriches our understanding of the universe and our place within it, inspiring awe and curiosity that transcend disciplines and generations. Gravitational wave background and black holes. Black holes, the enigmatic remnants of collapsed stars, are among the most significant contributors to the gravitational wave background, GWB. These cosmic behemoths, from stellar mass black holes to supermassive entities at galactic centers, create gravitational waves that reverberate across the universe. The collective signals from black hole interactions weave a complex tapestry that shapes the stochastic gravitational wave spectrum. Understanding their contributions offers profound insights into both individual black hole dynamics and the larger structure of the cosmos. When two black holes spiral inward and collide, they release an immense burst of gravitational energy. Events like GW 150914, the first observed gravitational wave, are now understood as just the tip of the iceberg in a sea of binary mergers occurring across cosmic history. These mergers not only produce powerful discrete waves, but also contribute to the continuous hum of the GWB. Each event leaves a distinct imprint, with its frequency and amplitude influenced by the masses and spins of the merging black holes. Intermediate mass black holes, often considered the missing link between stellar mass and supermassive black holes, play a unique role in generating stochastic signals. These elusive objects, typically ranging from hundreds to thousands of solar masses, are thought to form in dense environments like globular clusters. Their mergers generate gravitational waves at frequencies that bridge the gap between ground-based detectors like LIGO and space-based observatories like LISA. Detecting these intermediate mass mergers is critical for understanding their population and contribution to the GWB. Supermassive black hole binaries, found at the centers of galaxies, are another major contributor to the GWB. These behemoths, with masses millions to billions of times that of the Sun, form binaries during galactic mergers. As they orbit each other over millions of years, they emit low-frequency gravitational waves that combine into a persistent background signal. Pulsar timing arrays, PTAs, are particularly suited to detecting these signals, as they operate at the nanohertz frequencies where supermassive binaries dominate. The detection of these waves will offer unprecedented insights into galaxy formation and evolution. Gravitational wave bursts from hyperbolic encounters, where black holes pass close to each other without merging, add yet another layer to the GWB. These events, though rare, produce short, intense bursts of gravitational waves that enrich the stochastic background. Such hyperbolic interactions are more likely in dense regions like galactic cores or globular clusters, where black hole densities are high. The spin and mass ratios of black holes significantly affect the characteristics of the waves they produce. Highly spinning black holes, for instance, emit gravitational waves with unique polarization patterns and frequencies. Similarly, unequal mass binaries generate asymmetric waveforms with higher harmonics that distinguish them from equal mass systems. These subtle variations are encoded in the GWB, providing clues about the physical properties of black hole populations. Accretion disks surrounding black holes can also influence gravitational wave emission. In supermassive black hole binaries, the surrounding disk of gas and dust can alter the orbital dynamics, affecting the timing and amplitude of gravitational waves. Additionally, interactions between the accretion disk and the binary's gravitational field can produce secondary waveforms, further complicating the GWB. Primordial black holes, theorized to have formed shortly after the Big Bang, could contribute to the GWB in unique ways. These hypothetical objects, ranging from microscopic to stellar masses, might merge over cosmic timescales, adding to the stochastic background. If detected, signals from primordial black holes could provide a window into the universe's earliest moments, testing models of inflation and cosmic evolution. Gravitational wave echoes from exotic black hole horizons add another speculative but intriguing dimension. In some alternative theories of gravity, black holes may have fuzzy or non-standard horizons that produce echoes following the main gravitational wave event. These echoes, if detected, would challenge our understanding of black hole physics and contribute distinct features to the GWB. The interaction between black holes and dark matter halos is a frontier area of research. Dark matter's gravitational influence could alter black hole dynamics, subtly shifting the timing and amplitude of their gravitational waves. Additionally, dense dark matter halos might enhance the rate of black hole mergers, amplifying their contribution to the GWB. Insights from black hole evaporation, as described by Hawking radiation, add a quantum mechanical layer to GWB research. While the gravitational waves from such microscopic black holes would likely be too weak to detect with current technology, their theoretical inclusion in the GWB spectrum highlights the interplay between general relativity and quantum mechanics. The ring-down phase of black hole mergers creates unique imprints in the gravitational wave signal. This phase, where the merged black hole settles into a stable state, emits a decaying waveform that encodes information about the black hole's mass, spin, and structure. These ring-down signals contribute distinct harmonics to the GWB, enriching its complexity. Binary interactions involving black holes and neutron stars are another fascinating contributor to the GWB. These mixed binaries produce hybrid gravitational wave signatures, combining elements of both black hole and neutron star dynamics. Such systems are also key targets for multi-messenger astronomy, as they can emit electromagnetic radiation alongside gravitational waves. Black hole mergers seem to occur more frequently in globular clusters, which are dense groups of stars. Multiple black holes, which are common in these clusters, can interact and merge more rapidly than the average galaxy population. The significance of researching these stellar settings is underscored by the cumulative impact of these mergers on the GWB. Certain regions of space, referred to as stellar mass black hole factories, are thought to produce black holes at exceptionally high rates. These regions, often found in starburst galaxies or other active environments, contribute disproportionately to the GWB. Their study provides insights into the conditions that favor black hole formation and merger. Separating black hole signals from the GWB poses formidable but solvable detection issues in the future. With more sensitive detectors, it will be necessary to employ complex modeling and analytic techniques in order to differentiate between individual black hole events and the stochastic background. To extract the faint black hole signs from the GWB, advances in detection technology and computing capacity are required. The contributions of black holes to the GWB reveal the immense dynamism and complexity of the universe. From the rhythmic spirals of binary mergers to the faint echoes of primordial black holes, each signal adds a thread to the cosmic symphony. Impacts of GWB research on astrophysics. The study of the gravitational wave background, GWB, has become a transformative tool in astrophysics, offering profound insights into the universe's most enigmatic phenomena. Beyond the sheer wonder of detecting ripples in spacetime, GWB research has redefined our understanding of black holes, neutron stars, galaxy evolution, and the physics of compact objects. It serves as a bridge between theory and observation, enabling astrophysicists to test and refine models across a wide spectrum of cosmic scales. Gravitational wave data have refined the mass distribution of black holes and neutron stars. By analyzing the frequency and amplitude of signals contributing to the GWB, researchers can pinpoint the mass ranges of these compact objects, revealing previously unknown populations. For example, gaps in the mass spectrum, such as the hypothesized mass gap between neutron stars and black holes, have been scrutinized with GWB detections. This information reshapes models of stellar evolution and the processes leading to compact object formation. The GWB provides a unique lens for understanding cosmic star formation histories. Star formation directly correlates with the production of compact binaries, as massive stars end their lives as black holes or neutron stars. By studying the stochastic signals generated by mergers over cosmic time, astrophysicists can reconstruct the star formation rate in different epochs of the universe. This connection bridges observations of gravitational waves with optical and infrared surveys of star-forming galaxies, creating a unified picture of cosmic evolution. Galaxy mergers, which drive the assembly of supermassive black holes and trigger bursts of star formation, are another area enriched by GWB research. The low-frequency gravitational waves emitted by supermassive black hole binaries during galaxy mergers contribute prominently to the GWB. By correlating these signals with large-scale simulations of galaxy formation, researchers refine models of how galaxies grow and interact. These studies shed light on the frequency and outcomes of galactic collisions, illuminating the universe's large-scale structure. Compact object populations in dense stellar environments, such as globular clusters and galactic nuclei, are better understood through GWB analysis. These regions, where stars are packed densely, often become breeding grounds for black hole and neutron star mergers. The gravitational wave signals originating from such environments reveal their demographics, including the prevalence of intermediate mass black holes and the dynamical processes that drive mergers in crowded systems. Relativistic jets, often associated with active galactic nuclei and gamma-ray bursts, are tested against data from the GWB. Theoretical models of these jets, which are powered by supermassive black holes or neutron star mergers, predict specific gravitational wave emissions. By comparing these models with observed stochastic signals, astrophysicists validate or refine the mechanics behind jet formation, collimation, and energy output, adding a gravitational perspective to high-energy astrophysics. The early universe dynamics, particularly in the epochs following the Big Bang, leave imprints in the GWB. Primordial gravitational waves generated during inflation, phase transitions, or cosmic string dynamics contribute to the stochastic background at extremely low frequencies. These signals offer a direct probe of conditions that existed billions of years before the first stars and galaxies formed, opening a unique observational window into the universe's infancy. The assembly of supermassive black holes is one of the most intriguing mysteries addressed by GWB research. These titanic objects, often found at the centers of galaxies, grow through mergers and accretion. The gravitational waves emitted by merging supermassive black holes provide a record of their growth and interactions. By studying these contributions to the GWB, researchers unravel the evolutionary pathways that lead to the formation of the universe's most massive entities. Globular clusters, home to dense populations of stars and compact objects, are another area where GWB research is making strides. The gravitational wave signals from mergers within these clusters offer insights into their dynamical evolution, including the processes that drive black holes and neutron stars into close orbits. This data helps astrophysicists refine simulations of globular cluster evolution and understand their role in the larger galactic ecosystem. The identification of rogue stellar remnants, such as isolated black holes or neutron stars drifting through interstellar space, is assisted by the GWB. These objects, which lack electromagnetic signatures, can still emit faint gravitational waves if they are part of binary systems or interact with other masses. Detecting their contribution to the GWB offers a method for cataloging these elusive remnants, broadening our understanding of the compact object population. The GWB also provides a unique testbed for extreme physics, particularly within neutron star crusts. When neutron stars collide, the gravitational waves they emit carry imprints of the material properties of their ultra-dense cores and crusts. This allows researchers to place constraints on the equation of state of neutron star matter, refining our understanding of the behavior of matter at densities far exceeding those found in atomic nuclei. The evolution of galaxies is closely tied to the dynamics of their compact object populations, and GWB research expands our understanding of this relationship. The gravitational waves emitted by compact binaries reflect the history of star formation, supernova rates, and binary interactions within galaxies. By mapping these signals, astrophysicists develop more comprehensive models of how galaxies evolve over cosmic time. Dwarf galaxies, often overlooked in traditional surveys, offer unique insights through their gravitational wave signals. Compact binaries in these small, low-mass galaxies can contribute to the GWB, particularly if their merger rates or environments differ from those in larger galaxies. Correlating these contributions with other astrophysical data sheds light on the role of dwarf galaxies in the broader cosmic landscape. Magnetic fields interact with compact objects in ways that influence gravitational wave emissions. For example, the presence of strong magnetic fields around neutron stars can alter the dynamics of their orbits, changing the frequency and amplitude of emitted waves. The GWB provides an indirect method for studying these interactions, offering insights into the magnetic field strengths and configurations around compact objects. The cosmic distribution of compact binaries may also be seen on the GWB map. Astrophysicists may create a three-dimensional map of compact binary populations across the universe by evaluating the anisotropies in the stochastic background, which in turn allows them to deduce the spatial distribution of gravitational wave sources. This information adds a new layer to our knowledge of the cosmic web and works in tandem with conventional astronomical surveys. The impacts of GWB research on astrophysics are profound and far-reaching. From probing the earliest moments of the universe to refining our models of compact object dynamics, gravitational wave data enrich every facet of astrophysical inquiry. As detectors become more sensitive and datasets grow, the GWB will continue to serve as a vital tool for unlocking the universe's most complex mysteries, bridging gaps between theory and observation, and deepening humanity's understanding of the cosmos. Challenges in isolating GWB signals. Isolating the gravitational wave background, GWB, from the multitude of noise sources that plague observational data is one of the most complex tasks in modern astrophysics. While detecting gravitational waves has become increasingly sophisticated, the stochastic nature of the GWB, its faint, overlapping signals, poses unique challenges. Addressing these challenges requires innovative techniques, robust instrumentation, and interdisciplinary collaboration. In ground-based observatories like LIGO and Virgo, distinguishing GWB signals from background noise is a major challenge. Noise at low frequencies can obstruct GWB signals. This noise can be produced by tremors from earthquakes, cars, and even tiny movements in the Earth's crust. Though sophisticated seismic isolation devices and subterranean detector locations assist reduce the impact of this interference, it cannot be totally eliminated. Atmospheric changes caused by weather can amplify background noise, further obscuring the already low stochastic signals. Space-based detectors such as the upcoming LISA face their own challenges, particularly interference from instrumental noise. Thermal fluctuations, stray magnetic fields, and imperfections in laser stability can contaminate the data. These issues demand stringent calibration protocols and materials engineered to withstand the extreme conditions of space. The push to enhance laser precision and maintain strict temperature control is critical for reducing noise in these ambitious space missions. Differentiating the GWB from individual, loud gravitational wave events is another significant obstacle. Binary black hole mergers or neutron star collisions produce sharp, detectable signals that can overshadow the diffuse background. Advanced algorithms must filter out these transient events to reveal the underlying stochastic pattern of the GWB. However, distinguishing between a superimposed series of individual signals and true background noise often requires iterative data processing techniques, which are computationally intensive. Astrophysical clustering introduces anisotropies in the GWB, complicating its interpretation. Regions with dense populations of compact binaries, such as galactic centers, create localized enhancements in gravitational wave intensity. These anisotropies need to be modeled and corrected to extract isotropic background signals. This effort requires integrating data from electromagnetic observations of galactic structures and star formation histories to predict clustering effects accurately. Recognizing GWB signals across a wide frequency range is difficult because detector sensitivity changes with frequency. Pulsar timing arrays are more suited to low-frequency transmissions, whereas ground-based observatories are great at picking up high-frequency waves. To close this gap, we need to use methods from different fields and calibrate detectors thoroughly so that their sensitivity is consistent. Important messages risk being misunderstood or ignored in the absence of such harmony. Foreground noise, such as emissions from galactic binaries, can obscure the stochastic signals of the GWB. These foreground sources create overlapping waveforms that mimic the background signal, making them difficult to distinguish. Statistical techniques, such as matched filtering and Bayesian inference, are employed to separate these sources, but they depend on accurate modeling of foreground populations. Low-frequency GWB signals are particularly susceptible to interference from local galactic sources, such as close binary stars in the Milky Way. These sources dominate the frequency bands targeted by pulsar timing arrays, creating a noisy environment. To address this, researchers must develop filtering algorithms that account for the unique spectral characteristics of local sources, ensuring the true GWB signal is not drowned out. Solar system ephemeris perturbations introduce additional complications. Variations in the orbits of planets, particularly massive ones like Jupiter, can affect the timing precision of pulsar observations. These perturbations create subtle shifts in the data, which must be meticulously corrected using precise models of planetary motion. Failure to account for these effects can lead to spurious results in GWB studies. Errors in pulsar timing models pose another significant challenge. Timing arrays rely on extreme precision, often down to nanoseconds, to detect gravitational wave effects. However, uncertainties in the spin-down rates of pulsars, interstellar medium dispersion measures, and intrinsic pulsar glitches can introduce timing errors that mimic or mask GWB signals. Continuous monitoring and updated models are essential to mitigate these issues. Cross-checking GWB detections with data from multiple observatories provides an effective strategy for reducing false positives. By comparing results from ground-based interferometers, space-based detectors, and pulsar timing arrays, researchers can validate the presence of a GWB signal. This collaborative approach enhances confidence in detections while identifying systematic discrepancies between datasets. Theoretical uncertainties in modeling the GWB further complicate detection efforts. Predicting the exact spectral shape and amplitude of the background depends on assumptions about binary merger rates, star formation histories, and exotic sources like cosmic strings. Any inaccuracies in these models can lead to mismatches between theoretical predictions and observed data. Iterative refinement of models based on empirical findings is therefore a cornerstone of GWB research. Blind searches for isotropic GWB signals demand robust algorithms capable of detecting patterns without prior assumptions. These algorithms must identify weak, diffuse signals buried within noisy datasets. Machine learning techniques are increasingly employed to enhance these searches, but their application requires extensive training on simulated data to avoid overfitting or bias. Quantum noise imposes a fundamental limit on the sensitivity of gravitational wave detectors. This noise arises from the uncertainty principle, affecting the measurement precision of laser interferometers. Advanced quantum squeezing techniques are being developed to reduce this limitation, but achieving practical implementation on a large scale remains a significant hurdle. Detector downtime disrupts continuous data collection, creating gaps that complicate the long-term analysis required for GWB studies. Scheduled maintenance, hardware failures, and environmental events all contribute to these interruptions. Data interpolation methods are employed to bridge these gaps, but they introduce uncertainties that must be accounted for in the final analysis. Systematic biases in GWB studies, whether from instrumentation, data processing, or modeling assumptions, require long-term strategies for mitigation. Regular calibration, cross-disciplinary collaboration, and transparent sharing of methodologies are essential for addressing these biases. As detection methods evolve, so too must the protocols for ensuring the reliability of results. The challenges in isolating GWB signals are daunting, but they underscore the sophistication and resilience of modern astrophysics. Overcoming these obstacles demands not only technical ingenuity, but also global collaboration among observatories and theoretical researchers. Gravitational wave background and dark matter. The perplexing nature of dark matter continues to test and broaden our knowledge of the universe. Its interactions with gravitational waves, particularly within the stochastic gravitational wave background, GWB, provide new opportunities to investigate both phenomena. Scientists are discovering small but fundamental linkages between dark matter and gravitational wave signals, which might transform our understanding of the universe's hidden components. Dark matter halos, the massive invisible structures that envelop galaxies, play a significant role in gravitational wave propagation. These halos can act as lenses, bending spacetime and altering the paths of gravitational waves as they traverse the cosmos. This lensing effect introduces delays or amplifications in wave signals, providing a unique opportunity to study the distribution and density of dark matter. By correlating these distortions with known dark matter profiles, researchers can refine their models of halo structures and their interactions with visible matter. The potential interactions between ultralight dark matter particles and gravitational waves add another layer of complexity to this relationship. Ultralight dark matter, a hypothesized form of matter with masses billions of times smaller than electrons, could create oscillatory distortions in spacetime. These distortions might leave imprints on gravitational waves, altering their frequencies or amplitudes. Detecting such subtle changes would not only confirm the existence of ultralight dark matter, but also provide a direct means of probing its properties. Gravitational waves offer a powerful tool for detecting signals from dark matter clumps interacting with compact objects like black holes or neutron stars. These interactions could generate unique transient gravitational wave signatures. For instance, when a dense clump of dark matter passes close to a black hole, it could induce resonances or perturbations in the surrounding spacetime, producing detectable ripples. Such events could reveal the nature and behavior of dark matter on small scales. Dark matter annihilation, a phenomenon predicted by some theories, might contribute to the stochastic GWB. In regions of high dark matter density, particle-antiparticle pairs could annihilate, releasing energy in the form of gravitational waves. These signals, though faint, would add to the cumulative background noise, providing a unique fingerprint of dark matter interactions. Identifying such contributions requires distinguishing them from other sources, a task that demands highly sensitive detectors and robust statistical models. The GWB spectra are also heavily influenced by primordial black holes, which have been postulated as possible sources of dark matter for a long time. During cosmic history, different gravitational wave signals would have been added to the background if primordial black holes constituted a significant portion of dark matter. By analyzing these waves, researchers can find out how massive primordial black holes were and how often they merged, as well as whether or not they behaved like dark matter. Dark matter substructures, such as dense clumps or filaments, influence gravitational wave lensing in measurable ways. These substructures can create localized distortions in the gravitational wave signals passing through them, leading to detectable anomalies. By mapping these distortions, researchers can build a more detailed picture of dark matter's distribution on galactic and intergalactic scales. Correlating dark matter density distributions with anisotropies in the GWB offers insights into how large-scale cosmic structures affect gravitational wave propagation. Regions of high dark matter concentration, such as galactic clusters, may produce localized enhancements or deficits in the GWB signal. These anisotropies provide a complementary method for studying the relationship between dark matter and gravitational waves. Gravitational wave signals from dark matter accretion around compact objects present another intriguing avenue for research. As dark matter accumulates near black holes or neutron stars, its gravitational effects could generate unique waveforms. These signals might carry information about the density, distribution, and composition of the accreted dark matter, offering clues about its elusive nature. Under some circumstances, exotic dark matter particles like axions or WIMPs, weakly interacting massive particles, might potentially add to the phenomenon of gravitational wave emission. The waveforms produced by these particles' interactions with compact things could be different from those of baryonic matter. A direct connection between gravitational waves and the dark side of physics may be established if such signals could be detected. Globular clusters, dense groupings of stars and compact objects, serve as natural laboratories for probing dark matter using gravitational waves. If dark matter is present within these clusters, its interactions with compact binaries could influence their gravitational wave emissions. By studying these emissions, researchers can infer the amount and distribution of dark matter within such clusters. Cosmic strings, hypothetical one-dimensional defects in spacetime, might emit gravitational waves influenced by their interactions with dark matter. These interactions could alter the string's oscillation modes, creating unique contributions to the GWB. Testing such scenarios would provide insights into both cosmic strings and the role of dark matter in shaping their dynamics. Theoretical frameworks in the dark sector, including modified gravity theories and hidden dimensions, can be tested with gravitational wave data. These theories often predict deviations in the GWB's spectral properties, offering a means to validate or refute them. Gravitational waves thus serve as a bridge between observational astrophysics and theoretical physics, enabling tests of cutting-edge hypotheses. Another unusual addition to the GWB are axion clouds, which are created by revolving black holes. As they change over time, these clouds, made of theoretical particles anticipated by certain extensions of the Standard Model, may release gravitational waves. The detection of these emissions would establish the reality of axions and establish an empirical connection between particle physics and astronomy. Sterile neutrinos might generate gravitational waves under specific conditions. For instance, their decay or interactions with baryonic matter could produce transient waveforms. Exploring these possibilities requires highly sensitive detectors and advanced modeling techniques, but the potential rewards include breakthroughs in understanding the nature of dark matter. Good things are on the horizon for connecting GWB results to dark energy and dark matter. Although dark energy is most commonly linked to the acceleration of the expansion of the universe, it may have an impact on the propagation of gravitational waves through its interactions with dark matter. Researchers may find new links between the most enigmatic parts of the cosmos by analyzing these impacts. The interplay between dark matter and the GWB represents a frontier in astrophysical research. As detectors become more sensitive and theoretical models more refined, the potential for groundbreaking discoveries grows. By exploring these connections, we move closer to unraveling the mysteries of dark matter and its profound impact on the fabric of spacetime. Interdisciplinary applications of GWB research. The discovery and study of the gravitational wave background, GWB, extend far beyond astrophysics, influencing a wide array of disciplines. This interconnected nature of GWB research exemplifies how understanding the cosmos often leads to advancements in seemingly unrelated fields. By exploring these interdisciplinary applications, we can appreciate the broader implications of gravitational wave discoveries. Gravitational wave data offer an unprecedented opportunity to refine cosmological models of the early universe. The stochastic GWB carries imprints from epochs such as inflation and the subsequent phase transitions, providing a direct observational link to these formative periods. By integrating GWB data into existing models, scientists can test the accuracy of their predictions about the density fluctuations and energy scales that governed the universe's birth. These refinements help bridge the gap between theory and observation, advancing our understanding of cosmic origins. GWB research has the potential to make significant contributions to theories of quantum gravity. At extremely high energies, gravitational waves provide a novel approach to studying the quantum mechanical and general relativity quantum interaction. Examples of such phenomena include loop quantum gravity and string theory, which may be better understood if anomalies in GWB spectra were to point to impacts from quantum spacetime structures. An essential step toward a unified theory is this merging of macroscopic and microscopic physics. The GWB also informs the study of high-energy particle physics. Processes like cosmic string formation or particle annihilation in the early universe can leave detectable signatures in the GWB. These signals act as indirect evidence of particles and interactions that are otherwise inaccessible to particle accelerators. By analyzing the energy distribution and polarization of gravitational waves, physicists can test models of supersymmetry, axions, or other beyond standard model particles. Astrophysical models of galaxy formation benefit significantly from GWB studies. The gravitational wave signals generated by mergers of supermassive black holes and compact binaries provide insights into the hierarchical assembly of galaxies. By correlating these events with observational data on galaxy clustering and star formation rates, researchers can refine models that describe the evolution of cosmic structures over billions of years. Alternative theories of gravity are another area where GWB data play a critical role. Deviations from the predicted waveforms or propagation speeds in general relativity could indicate the presence of modified gravitational laws, such as scalar tensor theories or higher dimensional models. Testing these alternatives is vital for addressing unresolved issues like dark energy or the cosmological constant problem. Dark energy, the mysterious force driving the accelerated expansion of the universe, may also intersect with GWB research. Gravitational waves propagating through regions dominated by dark energy could experience subtle distortions, offering a new way to constrain its properties. This interdisciplinary approach merges cosmology and astrophysics, shedding light on one of the universe's greatest mysteries. Theoretical hints about multiverse ideas might be one of the most nebulous uses of GWB signals. Gravitational waves from nearby bubble universes might perhaps faintly imprint the GWB according to some inflationary theories. Even if it's still very difficult to detect such signs, the prospect opens up new avenues of inquiry into theoretical physics and the nature of reality. GWB research has inspired advancements in computational mathematics, particularly in signal processing and data analysis. The techniques developed to filter stochastic gravitational wave signals from noise have applications in fields ranging from telecommunications to medical imaging. For example, wavelet transforms and machine learning algorithms refined for GWB analysis are now finding use in other high-dimensional data environments. Educational outreach has flourished as a result of the excitement surrounding GWB discoveries. From captivating visualizations of spacetime ripples to interactive simulations, gravitational wave research has become a cornerstone of public engagement in science. These efforts inspire the next generation of scientists while fostering a broader appreciation for the complexities of the universe. The precision instrumentation used in gravitational wave observatories has also contributed to advancements in geophysical techniques. For instance, laser interferometry, initially developed for LIGO, is now being adapted to detect subtle shifts in Earth's crust, aiding in earthquake monitoring and exploration of underground resources. This cross-disciplinary application highlights the practical benefits of fundamental research. Space exploration technologies are poised to benefit from GWB studies as well. Advanced materials and vacuum isolation techniques developed for detectors like LISA could be applied to spacecraft design, enhancing durability and performance in extreme environments. Additionally, gravitational wave navigation systems might one day assist in interstellar travel, providing a novel method for orientation using cosmic signals. Intersection with GWB research are theoretical investigations of spacetime discreteness, a notion that proposes quantization of spacetime at the Planck scale. The existence of underlying features or pixels in spacetime might be suggested by deviations from smooth waveforms. The detection of such outliers would provide a novel connection between gravitational wave observations and the quantum mechanical underpinnings. Acoustic modeling has also been expanded through gravitational wave analogues. The mathematical similarities between sound waves and gravitational waves have inspired innovations in noise cancellation, architectural acoustics, and even medical ultrasound technology. This unexpected connection illustrates the far-reaching influence of GWB research. Artificial intelligence, AI, and machine learning have become indispensable tools in analyzing gravitational wave data. AI algorithms help identify weak signals buried in noise, automate data processing pipelines, and optimize detector performance. The interplay between GWB research and AI development is fostering innovation in both fields, with applications ranging from autonomous vehicles to climate modeling. The study of the GWB exemplifies the power of multidisciplinary collaborations. Scientists from astrophysics, particle physics, computer science, and engineering come together to tackle the challenges of gravitational wave detection and interpretation. These collaborations not only enhance scientific progress, but also demonstrate the importance of global teamwork in addressing complex questions. Gravitational wave background research continues to push the boundaries of human knowledge, offering profound insights into the workings of the universe while driving advancements across diverse fields. From refining our understanding of the early cosmos to improving everyday technologies, the interdisciplinary applications of GWB research underscore its transformative potential. This journey of discovery is a testament to the interconnectedness of scientific inquiry and its capacity to reshape our world. Anisotropies and GWB mapping. The gravitational wave background, GWB, is often envisioned as an isotropic hum, a uniform signal emanating from countless cosmic sources. However, subtle variations, anisotropies, in this background offer a wealth of information about the large-scale structure of the universe. By mapping these anisotropies, scientists can uncover the imprints of galaxy clustering, cosmic voids, and even primordial fluctuations, pushing the boundaries of what gravitational wave astronomy can reveal. Anisotropies in the GWB provide a window into the universe's large-scale structure. Just as the cosmic microwave background, CMB, carries imprints of density fluctuations from the early universe, the GWB reflects the spatial distribution of gravitational wave sources. Galaxy clusters, filaments, and voids leave distinct signatures in the gravitational wave spectrum, creating a cosmic map etched into the fabric of spacetime. Detecting and characterizing these anisotropies requires advanced techniques and precise measurements. Interferometric detectors like LIGO and Virgo, while primarily designed for transient events, can contribute to GWB mapping by integrating long-term data to identify directional variations. Space-based detectors such as LISA promise even greater sensitivity to anisotropies by spanning a broader frequency range and enabling all-sky coverage. Statistical tools like spherical harmonics are crucial in decomposing the GWB into anisotropic components, revealing patterns that point to specific cosmic structures. The clustering of galaxies plays a significant role in shaping GWB anisotropies. Massive structures like galaxy superclusters generate gravitational waves from their dense populations of compact objects, such as merging black holes and neutron stars. The resulting anisotropies reflect the uneven distribution of these systems, providing clues about the underlying matter distribution. Conversely, cosmic voids, vast regions of low density, create regions where the GWB signal diminishes, offering a stark contrast to the peaks associated with clustered galaxies. Cosmic voids themselves offer intriguing insights when studied through gravitational wave propagation. As waves travel through these sparse regions, they may experience subtle distortions or frequency shifts, adding complexity to the observed anisotropies. By mapping these effects, researchers can gain a deeper understanding of the universe's underdense regions and their role in cosmic evolution. Angular resolution is key to effective GWB mapping. Current detectors provide limited directional sensitivity, but next-generation observatories aim to refine this capability significantly. High angular resolution allows scientists to pinpoint the locations of gravitational wave sources, distinguishing between contributions from galactic and extragalactic origins. This precision is essential for correlating gravitational wave signals with electromagnetic observations and enhancing the multi-messenger approach to astrophysics. It is also possible that cosmic string networks, which are remnants of early universe phase transitions, contribute to GWB anisotropies. A possible outcome of these made-up structures' geographical dispersion is the formation of directed imprints caused by bursts of gravitational waves. Not only would finding such anisotropies prove the presence of cosmic strings, but it would also provide insight into basic physics on scales of energy that particle accelerators cannot achieve. The ability to differentiate between galactic and extragalactic contributions is a cornerstone of GWB anisotropy studies. Galactic sources, such as compact binaries within the Milky Way, produce a distinct foreground signal that must be separated from the isotropic and anisotropic components originating from distant sources. Techniques like spectral decomposition and cross-correlation with electromagnetic data are vital for disentangling these layers, ensuring a clearer picture of the GWB's extragalactic origins. Correlating GWB anisotropies with electromagnetic observations opens new avenues for exploring the cosmos. For instance, gravitational wave hotspots can be cross-referenced with known galaxy clusters or active galactic nuclei, linking specific sources to observed anisotropies. This synergy between gravitational and electromagnetic data enhances our understanding of the astrophysical processes driving the GWB, bridging gaps between different observational domains. Primordial density fluctuations, the seeds of cosmic structure, also leave their mark on the GWB. These fluctuations, amplified during inflation, produce variations in the gravitational wave signal that align with the distribution of matter in the early universe. Mapping these imprints provides a unique way to probe the conditions of the primordial cosmos, complementing insights gained from the CMB and large-scale structure surveys. Refining models of gravitational wave propagation is another critical outcome of anisotropy studies. Variations in the intergalactic medium, such as turbulence or density fluctuations, can distort gravitational wave signals, altering their anisotropic patterns. By accounting for these effects, scientists can develop more accurate propagation models, ensuring that observed anisotropies reflect the true distribution of sources. Directional signals in the GWB can even be used to map dark matter distributions. Gravitational waves passing through dark matter halos experience subtle lensing effects, creating detectable anisotropies that trace the invisible scaffolding of the universe. This innovative approach offers a new tool for studying dark matter, complementing traditional methods like galaxy rotation curves and weak lensing surveys. The future of anisotropy detection depends on advancements in detector technology. Space-based observatories like LISA will provide unparalleled sensitivity to low-frequency gravitational waves, enhancing the resolution of anisotropic maps. Proposed designs for ground-based detectors, such as the Einstein telescope, also aim to improve angular resolution and sensitivity, enabling detailed studies of GWB anisotropies across a wide frequency range. Galactic dynamics play a significant role in shaping anisotropic GWB signals. The motion of the Milky Way through the cosmic web, for example, creates dipole anisotropies in the GWB, analogous to the CMB dipole, caused by Earth's motion relative to the CMB rest frame. Understanding these dynamics helps isolate intrinsic anisotropies from those induced by local motion, refining the interpretation of gravitational wave maps. Perhaps one of the most exciting prospects in GWB anisotropy research is the potential to identify unique sources within the stochastic background. Localized hotspots in the GWB map could correspond to rare events like hypermassive black hole mergers or cosmic string bursts. Detecting and characterizing these sources would provide invaluable insights into extreme astrophysical phenomena, pushing the boundaries of gravitational wave science. Mapping the anisotropies of the GWB is a transformative endeavor, revealing the universe's structure and dynamics in unprecedented detail. By combining advanced detection techniques, interdisciplinary approaches, and next-generation observatories, researchers are poised to unlock the secrets encoded in these subtle variations. Advanced detection techniques for the gravitational wave background. The pursuit of detecting the gravitational wave background, GWB, has driven the development of cutting-edge techniques and technologies, pushing the boundaries of physics and engineering. The complexity of capturing the faint stochastic signals that make up the GWB requires innovative methods that transcend traditional detection frameworks. From leveraging quantum mechanics to implementing artificial intelligence, these advancements are reshaping the landscape of gravitational wave astronomy. Quantum-enhanced gravitational wave detectors represent one of the most promising frontiers in improving sensitivity. By exploiting the principles of quantum mechanics, these detectors minimize noise that would otherwise obscure faint gravitational wave signals. Squeezed light states, for instance, are a breakthrough in noise reduction. These states reduce quantum uncertainty in one property of light, such as phase, while allowing greater uncertainty in another, like amplitude. This trade-off improves the precision of measurements without violating quantum principles, effectively enhancing the sensitivity of detectors like LIGO and Virgo. Incorporating optical lattice clocks into gravitational wave detection systems is another transformative approach. These clocks, which are among the most precise timekeepers known to science, can measure time intervals with incredible accuracy. When integrated into detection systems, they enable ultra-precise timing of signals, which is essential for isolating the subtle variations caused by gravitational waves. Optical lattice clocks promise to refine the synchronization of observatories, paving the way for more accurate cross-correlations and signal detections. Cross-correlation methods have emerged as a cornerstone in isolating stochastic GWB signals. By comparing data from multiple detectors, scientists can distinguish genuine gravitational wave signals from local noise. These methods rely on statistical analysis to identify patterns consistent across observatories, ensuring that the detected signals originate from cosmic sources rather than terrestrial interference. Cross-correlation is particularly valuable for detecting low-frequency waves that lie below the sensitivity range of individual detectors. Bayesian inference techniques have also revolutionized GWB signal analysis. By applying probabilistic frameworks, researchers can model uncertainties and extract signals buried in noise with greater confidence. Bayesian methods allow scientists to incorporate prior knowledge, such as expected waveforms or source distributions, into their analyses, enhancing the ability to distinguish stochastic signals from background noise. These techniques have become integral to gravitational wave astronomy, enabling more robust detections and interpretations. Space-based interferometers, such as the Laser Interferometer Space Antenna, LISA, hold unique advantages for detecting low-frequency components of the GWB. Operating in space eliminates many of the environmental challenges faced by ground-based observatories, such as seismic noise and atmospheric disturbances. LISA's ability to detect gravitational waves with wavelengths far longer than those accessible to terrestrial detectors makes it a vital tool for exploring the low-frequency regime, where signals from supermassive black hole mergers and cosmic strings reside. Earth's rotation is another factor leveraged to refine directional sensitivity in gravitational wave observatories. As Earth rotates, the relative orientation of a detector to incoming gravitational waves changes, providing a natural mechanism for enhancing directional resolution. This rotational modulation enables scientists to pinpoint the origins of gravitational waves with greater precision, particularly in the context of stochastic backgrounds. Artificial intelligence, AI algorithms, have become indispensable for pattern recognition in GWB data. These algorithms can analyze massive datasets, identifying subtle patterns that human analysts might overlook. Machine learning models, trained on simulated gravitational wave signals, excel at distinguishing stochastic signals from noise, improving the efficiency and accuracy of detection efforts. AI-driven tools are also being developed to predict potential signal candidates, optimizing the allocation of computational resources for follow-up analyses. High-frequency gravitational wave detectors are a niche but growing field, targeting signals beyond the reach of traditional interferometers. These detectors focus on the high-frequency end of the GWB spectrum, where signals from exotic sources such as primordial black hole evaporation or phase transitions in the early universe may reside. The development of these detectors expands the range of frequencies accessible to gravitational wave astronomy, opening new windows into the cosmos. Multiband detection strategies aim to capture overlapping sources across different frequency ranges. By combining data from ground-based observatories, space-based interferometers, and pulsar timing arrays, scientists can construct a more comprehensive picture of the GWB. This multiband approach is akin to observing the universe in multiple wavelengths of light, providing a richer understanding of the sources and dynamics contributing to the gravitational wave background. Atom interferometry, a novel technique, offers the potential for gravitational wave telescopes with unparalleled sensitivity. By using ultra-cold atoms to measure spacetime distortions, atom interferometers can detect gravitational waves with extraordinary precision. These devices are particularly promising for future space missions, where their compact size and high sensitivity could enable groundbreaking discoveries. Mitigating environmental noise remains a critical challenge for next-generation ground-based detectors. Advanced isolation systems, such as vacuum chambers and active feedback mechanisms, help reduce the impact of seismic, thermal, and acoustic disturbances. Materials engineering also plays a role, with researchers developing ultra-stable mirrors and suspension systems that minimize vibrations and thermal fluctuations. Pulsar timing precision is essential for long-term GWB studies, particularly for detecting nanohertz frequency waves. Millisecond pulsars, which serve as cosmic clocks, require timing measurements accurate to within nanoseconds to detect the subtle distortions caused by gravitational waves. Advances in radio telescopes and timing algorithms are continually improving the precision of pulsar timing arrays, enhancing their ability to contribute to GWB research. Gravitational wave triangulation involves using a network of global observatories to pinpoint the origins of detected signals. By measuring the arrival times of gravitational waves at different detectors, scientists can triangulate the direction of the source. This technique is invaluable for studying anisotropies in the GWB and identifying specific regions of the sky where signals are most concentrated. Quantum gravitational wave sensors represent the next frontier in detection technology. These sensors, which leverage quantum effects to achieve unprecedented sensitivity, could revolutionize gravitational wave astronomy. Concepts like quantum entanglement and superposition are being explored to enhance the precision of measurements, potentially enabling the detection of signals currently beyond the reach of existing technologies. The future of GWB detection lies in the convergence of these advanced techniques and technologies. Each innovation, from quantum enhancements to AI-driven analysis, adds a vital piece to the puzzle of understanding the stochastic gravitational wave background. As these methods evolve, they promise to unlock new levels of sensitivity, resolution, and insight, bringing us closer to unraveling the cosmic symphony encoded in gravitational waves. Gravitational wave background and the expanding universe. The gravitational wave background, GWB, is not only a repository of cosmic events, but also a profound tool for studying the dynamic fabric of the universe. Encoded within its faint stochastic signals are clues about the universe's expansion from its earliest moments to its current accelerating phase. By analyzing these waves, researchers are unlocking new insights into the universe's history, structure, and ultimate fate. Gravitational waves carry imprints of the universe's expansion rate, offering a direct probe of cosmological dynamics. The stretching of spacetime as the universe expands affects the frequencies of gravitational waves, much like the redshifting of light. These shifts encode information about the Hubble constant, a crucial parameter describing the current rate of cosmic expansion. By comparing GWB data to electromagnetic observations, researchers aim to resolve persistent tensions in determining the Hubble constant, such as the discrepancies between measurements from the cosmic microwave background, CMB, and supernova studies. The GWB provides a unique perspective on the universe's deceleration and acceleration phases. During the deceleration phase, dominated by matter and radiation, gravitational wave frequencies evolved differently compared to the current acceleration phase, driven by dark energy. By studying these changes, researchers can map the transition between these epochs, refining models of cosmic expansion and testing predictions of general relativity on cosmological scales. Changes in the universe's scale factor, describing how distances between cosmic objects expand over time, are directly linked to the frequencies of gravitational waves. Waves generated in the early universe have been stretched over billions of years, providing a natural timeline of expansion. Analyzing these stretched frequencies allows scientists to reconstruct the history of the universe's size and rate of growth, adding a gravitational perspective to traditional light-based observations. Gravitational waves also serve as probes of cosmic inflation, the brief period of exponential expansion that occurred fractions of a second after the Big Bang. Inflation is predicted to produce a spectrum of primordial gravitational waves, which contribute to the GWB. These waves carry information about the inflationary energy scale, the dynamics of the inflationary field, and potential deviations from the simplest inflationary models. By detecting and characterizing these primordial waves, researchers aim to uncover the physics driving this transformative epoch. Dark energy, the mysterious force accelerating the universe's expansion, remains one of the greatest puzzles in modern cosmology. The GWB provides an indirect probe of the dark energy equation of state, describing its behavior over time. Variations in gravitational wave frequencies, as influenced by dark energy's dominance, offer clues about whether dark energy is a cosmological constant, as in the LCDM model, or something more dynamic. These insights help refine our understanding of the underlying nature of this enigmatic component of the universe. Primordial gravitational waves, originating during the early universe, offer a wealth of information about cosmic dynamics. Unlike electromagnetic signals, which are absorbed and scattered, gravitational waves interact weakly with matter, preserving their original properties. These waves provide a pristine view of the universe's infancy, revealing the conditions and processes at play during its first moments. Such observations complement studies of the CMB, adding a gravitational dimension to our understanding of the universe's origins. The GWB also allows researchers to explore potential cyclic models of the universe, where periods of expansion and contraction occur in succession. In these models, gravitational waves generated during previous cycles could leave detectable imprints in the GWB. Analyzing these signals could provide evidence for or against cyclic cosmologies, challenging or validating the notion of a singular Big Bang origin. Large-scale structures, such as galaxy clusters and cosmic filaments, influence the propagation of gravitational waves. As waves travel through these dense regions, their amplitudes and phases are subtly altered. These interactions provide insights into the growth and distribution of large-scale structures, adding a gravitational lens to studies of the universe's architecture. By mapping these effects, researchers can refine models of structure formation and evolution. The LCDM model, which describes the universe as composed of dark energy, dark matter, and ordinary matter, is the foundation of modern cosmology. However, gravitational wave data offers a unique avenue for testing modifications to this model. Whether exploring alternative dark energy models, testing the validity of general relativity on cosmic scales, or probing the interplay between dark matter and ordinary matter, the GWB serves as a critical testbed for theoretical innovations. Redshift-dependent observations of the GWB shed light on galaxy evolution over cosmic time. As gravitational wave signals are redshifted by the universe's expansion, their properties reflect the conditions of their origin. Observing how the GWB changes with redshift allows researchers to trace the formation and merger rates of galaxies and compact objects, providing a dynamic picture of galactic evolution. The potential correlations between CMB anisotropies and the GWB open new interdisciplinary avenues. Both phenomena originate from the universe's early stages, with the CMB capturing fluctuations in the density of matter and the GWB recording the dynamics of spacetime itself. Comparing these datasets can reveal common origins, such as cosmic inflation, and identify unique contributions from gravitational phenomena. Gravitational waves might also reveal topological defects in the fabric of spacetime, such as cosmic strings or domain walls. These hypothetical features, remnants of symmetry-breaking phase transitions in the early universe, could emit distinctive gravitational wave signals. By identifying these signals in the GWB, researchers could provide direct evidence for these exotic structures, deepening our understanding of the universe's fundamental nature. The timeline of the reionization epoch, when the first stars and galaxies ionized the intergalactic medium, can be refined using GWB studies. Gravitational waves from compact object mergers during this period carry information about the rate and timing of reionization. By integrating GWB data with electromagnetic observations, researchers can construct a more detailed chronology of this transformative cosmic era. Gravitational waves, which propagate freely through spacetime, can potentially carry information from regions beyond the electromagnetic horizon. This capability offers a tantalizing glimpse into the unobservable aspects of the universe, expanding the boundaries of what we can know. The GWB is a powerful tool for probing the universe's expansion and evolution. Its signals encode the story of the cosmos, from the earliest moments of inflation to the ongoing acceleration driven by dark energy. As detection techniques advance and theoretical models improve, the GWB will continue to illuminate the hidden dynamics of the expanding universe, offering profound insights into the nature of spacetime, matter, and energy. Future prospects and legacy of GWB research. The study of the Gravitational Wave Background (GWB) has fundamentally transformed our understanding of the universe, providing insights into some of its most elusive phenomena. As we look ahead, the future of GWB research promises to expand these discoveries through groundbreaking observatories, interdisciplinary collaborations, and innovative technologies. Beyond the immediate scientific implications, GWB research is poised to leave a lasting legacy, reshaping humanity's relationship with the cosmos. The next generation of gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, and the Cosmic Explorer, will redefine the scope and sensitivity of GWB detection. LISA, operating in space, will target low-frequency gravitational waves inaccessible to ground-based detectors, unveiling signals from supermassive black hole mergers and early universe phenomena. The Cosmic Explorer, with its extended baseline and advanced technology, aims to capture faint stochastic signals with unprecedented clarity. Together, these observatories will expand the observable gravitational wave spectrum, providing a more comprehensive understanding of the GWB. Proposed projects like the Einstein Telescope, ET, represent another leap forward in gravitational wave astronomy. Designed to operate at cryogenic temperatures and shielded from seismic noise in underground facilities, the ET will enhance sensitivity to low-frequency signals and anisotropies in the GWB. Its ability to resolve overlapping signals from multiple sources will allow researchers to disentangle the complex tapestry of the GWB, identifying contributions from exotic astrophysical phenomena and primordial processes. The creation of gravitational wave communication systems is one of the most exciting potential outcomes of GWB studies. Although it is currently considered science fiction, the potential to use gravity waves as a means of communication has the potential to completely transform interplanetary communications by removing the constraints imposed by electromagnetic transmissions. The accuracy and creativity of present GWB detection methods have paved the way for such technologies, which may one day allow interference-free communication beyond cosmic distances. Establishing a global gravitational wave detection network will allow for continuous monitoring of the GWB, minimizing observational gaps and enhancing signal triangulation. Current partnerships, like those between LIGO, Virgo, and CAGRA, provide a model for how diverse observatories can work together. Future collaborations, involving countries with emerging space programs, will expand the global reach of GWB science, fostering a truly international pursuit of cosmic understanding. GWB research is expected to yield significant breakthroughs in our understanding of dark energy and dark matter. The interaction of gravitational waves with these mysterious components of the universe offers new avenues for probing their properties. For instance, GWB studies could help constrain the equation of state of dark energy, or reveal subtle interactions between dark matter halos and gravitational waves. These insights will complement other observational techniques, offering a multifaceted approach to unraveling the nature of these enigmatic forces. The integration of GWB signals with electromagnetic and neutrino observations will further elevate the role of multi-messenger astronomy. Events such as neutron star mergers, which emit gravitational waves, gamma rays, and neutrinos, highlight the power of combining diverse signals to build a holistic understanding of cosmic phenomena. As GWB detection becomes more precise, researchers will be able to cross-reference stochastic wave data with electromagnetic and neutrino sources, uncovering connections that would otherwise remain hidden. Gravitational wave research also holds promise for testing theories of quantum gravity. The stochastic nature of the GWB may carry imprints of quantum effects in spacetime, offering a rare opportunity to bridge the gap between general relativity and quantum mechanics. Observing these subtle features will push the boundaries of theoretical physics, potentially leading to a unified description of the universe's fundamental forces. Hypothetical boson stars, which are small objects made of scalar fields instead of regular matter, are one unconventional source of gravitational waves that future telescopes are anticipated to find. New types of matter and interactions anticipated by high-energy physics will be supported by these detections, which will put existing astrophysical theories to the test. We can learn more about the variety of cosmic objects when we include these sources in GWB investigations. The growing complexity of GWB research necessitates advancements in computational astrophysics. High-fidelity simulations of stochastic wave sources and their interactions with spacetime will become essential for interpreting observational data. By refining these models, researchers will enhance their ability to distinguish between overlapping signals, uncovering patterns that reflect the physical processes shaping the universe. As GWB studies interact with other areas of science, interdisciplinary research is going to thrive. For example, computational mathematics, signal processing, and material science are already being impacted by the tools created for gravitational wave detection. One example of how GWB research promotes partnerships outside of astrophysics and encourages technical innovation is the incorporation of AI algorithms into data analysis pipelines. The excitement surrounding GWB discoveries also has a profound impact on public engagement and education. Gravitational waves capture the imagination with their evocative names and mysterious origins, inspiring a new generation of scientists and enthusiasts. Outreach programs and accessible explanations of GWB research foster a sense of wonder and curiosity, encouraging broader participation in the scientific endeavor. The importance of ethical concerns will grow as GWB research propels technical progress. Thorough discussion is required to address concerns regarding the possible militarization of gravitational wave technology, the distribution of funds for basic research, and the far-reaching consequences of spacetime exploration. Scientists and politicians alike need to strike a balance between being insatiably curious and being good stewards of scientific advancement. The GWB serves as a unifying theme in humanity's exploration of the cosmos. Its signals transcend individual cultures and nations, reminding us of our shared place in the universe. Collaborative efforts to study the GWB exemplify the power of science to bridge divides and inspire collective action, fostering a sense of global unity in the face of cosmic vastness. The legacy of GWB research lies not only in its scientific achievements, but also in its capacity for unexpected discoveries. As detection techniques become more sensitive, researchers may uncover phenomena that challenge existing astrophysical models, prompting paradigm shifts in our understanding of the universe. The history of gravitational wave astronomy, from its theoretical roots to its transformative discoveries, underscores the importance of remaining open to the unknown. In the broader narrative of the 21st century, GWB research stands as a testament to humanity's drive to explore and understand. It connects us to the earliest moments of the universe, reveals the intricate workings of cosmic structures, and inspires visions of what lies beyond. The study of the GWB is not merely a scientific pursuit, but a profound exploration of our place in the cosmos, ensuring its enduring impact for generations to come. As we close this exploration of the gravitational wave background, we're reminded of the extraordinary ways science connects us to the mysteries of the cosmos, from the faint ripples of ancient cosmic events to the groundbreaking discoveries that await. The journey to understand gravitational waves is just beginning. If you've enjoyed delving into these cosmic wonders, don't forget to like, subscribe, and hit the notification bell to join us on future explorations. Thanks for watching.